No, I don't see Singla sir yet. Ashish Singla. Do you want
Okay,
to call him?
oh, I can start. I'm there, so I'll start. He can join later with me.
Anyway, I have sent you the slides with the
Okay,
table.
okay.
So we'll keep adding Amisha Bhaskar as speaker,
Yeah, yeah.
Nandani, Roma as speaker. Other three haven't checked. They were not Chinmay. Chinmay, Tanmay, Shivantan. So do you know anyone from paper ID 110?
Chinmay Samak, nobody is there.
Tanmay,
Omkar. Omkar is not here also.
one second.
Omkar. And
Omkar
Omkar.
also I couldn't see.
Oh no, this is Omkar Bange is the other. Omkar Jadhav is there. Yeah, he's there.
Okay, Omkar,
So we can make him
yeah,
add
speaker.
add to
Yeah,
stage, no?
yeah, I'm doing. And Udayan, he was
Then
there.
done it.
Okay, he's also there.
Okay, so only Chinmay is not there. I'll call him up.
Yeah, paper ID 110, sir. Maybe you can just check with Professor Singla also, if at all he's having any difficulty in logging in.
Good afternoon, sir. Ashish, sir. So, can
Yeah.
you
Yeah,
hear
you
me?
can. Yeah, Udayan, you start sharing and check.
Yeah. Okay.
Omkar Jadhav hasn't joined.
Okay,
He
Udayan,
can.
we see the slides. Okay.
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 Thank you.
What about
And
Omkar?
Omkar, please switch on your webcam, mic.
So, I just had a request from to Ashish, sir.
Mm-hmm.
Sir, actually, during the Q&A session, is it like possible that one of the co-authors can also like put in his ideas if required? He's present
Yeah,
in the meeting.
yeah. So, well, that's a little difficult because it will be in writing only.
Okay. Okay. Okay, sir.
Okay.
Fine.
Okay.
No,
Thank you.
if we want, we can ask them to come on stage. Is it okay?
That
Whatever is
that okay
comfortable, sir.
okay if required. If required.
Okay. Thank you, sir.
Yeah.
What Omkar is on? Omkar, can you
Yes.
check your slides? You have checked, right?
No, he hasn't checked.
No. Yeah, I can.
Chinmay is left. Chinmay.
Yes, Omkar, we can see. Can't go to the full screen.
Yeah. Yeah. Yeah.
No,
Can you
we
see?
don't see the full screen. Okay. Are you using Chrome?
Yes.
Okay. So what you do is come out of full screen,
Mm-hmm.
go to view and go to reading view. Go to view tab. Yeah, reading view. The left of it, left of it. Reading view. Fourth,
Yeah.
fifth. Yes.
Yeah.
Okay. Now, if you have any video, you can just check whether it works or not.
No, I don't have.
Okay, fine. So this is how you will have to present if at all it
Yeah.
doesn't go to full screen.
Yeah. Okay.
Okay, thank you.
Yeah.
I think we are set, sir. Unless that fourth, the other paper
Yeah,
ID
so
110.
I'll just call him once. Huh?
Okay,
Control F110.
you can stop, Omkar. Amisha, you may want to switch on webcam when we start because I am trying to take photo of all sessions in the beginning, all the speakers, so that we can at least have some virtual photo session.
If sir, during the presentation, if there is any sort of tech to avoid any technical issues, can we just keep the video off during the presentation?
Yes, that is fine.
Okay, thank you.
We will start exactly at 2, another 5 minutes.
Okay, Chinmay is just logging in. Huh?
Okay, sir. And do you want to try with Ashish, sir? Ashish Singla?
You have his number? I don't have his number.
I'll just reply back to the email then. Or maybe Ekta ma'am. No, I don't have his number. I'll just
Oh,
reply
okay.
back to the
Okay.
email.
No, I think we can start at 2 o'clock. Huh?
Okay.
How many people are there?
So you have the slides. Can you download the slide?
Yeah, I'll just do that.
So Chinmay, I'm yet to see him.
You send it to me now, or you send it to Ekta? Technical session 3, it says. Technical session.
Two also
okay,
I have
two
marked
also.
you.
Okay. Okay. So I just need to download the last file, right?
Yes. So first slide has table.
Hmm. Okay, so we have about 2 minutes left. Okay. So the speakers, please do keep in mind that you have 14 slides, and please finish your presentation in 14 minutes. Okay. Please finish your presentation in 14 minutes. And after that, we have 2 or 3 minutes of question answer. Okay. And the audience who are there, apart from the speakers, if you have any questions, you can write in the question answer section on the right side of your screen. On the right of your screen, you can see chat, you can see participants, you can see Q&A. So if you have any questions please, regarding the presentation, you can write the name of the paper, the number of the paper, okay, or the name of the author, and just write your question, okay, during the presentation. So the author can look at it and he can answer.
Yeah, Professor Ashish Singla has joined.
Okay. Okay, then he
Hello,
can.
hello, sir.
Yeah, hello. So he can take over the. So yeah, Ashish Singla, this. So we have 14 minutes per presentation,
Right, sir.
and 3 minutes of question answer after that. And the participants and the audience can write their questions in the Q&A section on the right side. And you can read the questions after the paper is presented, and the presenter can answer the questions. Okay, we should
Right.
finish each paper in say 18 to 19 minutes.
Sure, sir. Right.
Okay.
And regarding the template he has received, email.
Yeah, I have got the template. Yes.
Okay.
So okay, so you just have to give the marks also. Okay.
Yeah. Yes.
Okay. So we can start, I think, right? It's 2 o'clock.
Okay, sir. So welcome to all the dignitaries and all the participants in this session. So as mentioned by Professor Datta, so let's start with this second technical session on kinematics, dynamics, control and simulation of robotic systems. And so we'll invite the first speaker. So the paper ID is number 94, Roma Nandini, modeling and vision-based set point control of pneumatic-enabled robotic arm. So, Roma, are you there?
Yes, sir. I'll just share my presentation.
Yeah, yes, Roma, you are audible.
Okay. Okay, I'll start my presentation then.
Yeah, please go ahead. Yes.
Okay. Okay. Good afternoon, everyone. The topic of my work is modeling and vision-based set point control of pneumatic-enabled robotic arm. The motivation of my work was behind the idea of developing a rehabilitation robot and to analyze the usefulness artificial muscle, or generally it is say pneumatic muscle. So to get the usefulness of PAM in a rehabilitation robot, research has been carried out in the modeling and control of pneumatic muscle in a simple 2 degree of freedom setup. So I'll go with the contents. I'll start with the introduction, then literature review, problem statement, then manipulator setup as shown in the camera, then pneumatic system, then modeling of a pneumatic muscle will be covered. After that, modeling of pneumatic manipulator, and for the kinematics and dynamics. Lastly, we'll touch upon the control results and conclusion. So it started with the idea of working for the stroke patient. So as we know that stroke is one of the primary reason of impairment in a human body, and timely medical intervention has helped in lowering the death rates and disability among the patients. In addition to these traditional therapies, rehabilitation robots have come to rescue in providing a closely supervised, highly extensive exercises, or you can say repetitive exercises. So rehabilitation robots do much better than, equally better than the physiotherapists, because there are lesser chances of fatigue, which might be felt by a physiotherapist while doing the training. And these interaction with the robots can be made safer by using pneumatic actuator, because we understand that pneumatic actuators will soak up unwanted forces produced by the task. So it will help the patient when they are while they are executing the task. I'll cover some preliminary literature review. Uh, so I'll start with the planar manipulator arm. It is a single joint which has muscles, but the muscles are attached in an antagonistic way, which means that one of the muscle. So for one joint, there'll be two muscles, and one of the muscle acts in forward direction, and the other acts in the backward direction. And then we have another example, that is Rutgers Master 2. So this has single muscle actuators, but they are for the fingers, not for the arm. Then we have another pneumatic planar manipulator, which is very similar to the MIT Manus, which uses a uses normal actuators. But this one, this pneumatic planar manipulator has swivel module, and this uses two proportional pressure valves. So unlike other these above designs, our setup has the advantage that we are using reduced number of pneumatic muscles for each joint. The problem statement comes with the point that we want to develop a system which is a very low cost 2 degree of freedom manipulator, and we'll be applying a linear controller, that is PID controller. And as our objective was to use a contactless position sensor, so we'll use vision as a position sensor. So this is how the manipulator looks like from the camera. Uh, the camera is placed at the top at a fixed position, and it covers the complete workspace of the robot. So if we see that we have two joint positions, and these joint positions are continuously tracked by the camera using these Aruco markers. Then we have two pneumatic actuators. This is a pneumatic actuator 1 and 2. Then for each of the joints, we have attached a spring. So this is for spring 1, and the spring 2 is below this pneumatic actuators 2, so which is not visible at present from the camera. And Once we have this setup ready, we'll be moving on to the pneumatic system. So these two manipulators which are shown in the camera, these are these two muscles, and each of the muscles are joined by these binary valves. So these binary valves are on-off valves, and they are attached in one as an inlet valve and other as an outlet valve. So when the pressure is when the air is released, then the inlet valve gives in the air to the muscle, and outlet valve is responsible for releasing out the pressure. And between this air tank and inlet valve, we have a control system. We have a controller we have a microcontroller which actually let the binary, which gives the binary signals to these binary valves, which let them activate, which let them release the gates for to to get in the air, or let the air out of the system. Then we'll move on to the modeling of a pneumatic muscle. So as we can see, that force model of a muscle can be seen as a nonlinear spring force and nonlinear damper force from the equation 1. So nonlinear spring force is basically a static force which is derived from the geometrical construction, and nonlinear damper force is a frictional force due to the material arrangement in the muscle. From the equation 2, we will be using equation 2 for the force model of the muscle. And here the A1, A2, A3 till A8, these are the parameters which we'll find using experiments. And then we have epsilon, which is the delta of length. So L naught is the initial length of the actuator. So once the pressure is applied on the actuator, it compresses. And as it compresses, the length reduces. So the new length, that is L, is going to be the actuator's length after contraction. Now we'll move to the kinematics and dynamics part. So considering the forward kinematics, this is the setup for a, from the figure 3, you can see the two-link kinematic relation. L1, L2 are the joint length, and XC and YE are the end effector points. So this XC and YE equation, that is equation 3 and 4, are standard equations used for in forward kinematics, where if the angles are given, we can be using the geometrical relation, we can calculate the end effector positions. Here the important thing is that because the workspace is not the complete workspace of a normal two-link manipulator, so there is some resting position of both of the links, both of the joints. So this theta Ri is the angle obtained at the resting position of joint 1, and theta I is the change in the angle due to contraction of the muscle. So to get the change in angle, so we'll subtract the contraction, and we'll get this joint angle from the calculation from the camera frame. And the inverse kinematics for this is going to be the standard, I would say these are the standard equations for these theta 1 and theta 2 calculation, where we have link length, and it can be found that from the given theta positions, we can get the link lengths. We can get the joint angles. Now, considering the dynamics part, we are here assuming two things here. That the first one is the reaction forces on joint 1 due to joint 2 is going to be negligible, because the fixed end of the pneumatic actuator 2 is very close to the center of rotation of the joint 1. So we are considering it very negligible, and the coupling effects between the two joints are also ignored currently, because the system is it does not have too much speed, and the system is also lightweight, so we are ignoring the coupling effect. Considering these assumptions, we will equation assuming that we have not assuming, but considering that we have this, once we give pressure to the system of joint 1, then so this thing I have shown it, this force diagram is for the joint 1, and similarly this can be extended for the joint 2. So for the joint one, once the pressure, or you can say air, is released into the pneumatic muscle, then it compresses, and due to its compression, it moves in the anti-clockwise direction. Uh, in the driven gear, but with the driver gear, it moves in the clockwise direction. So the system is trying to move in the clockwise direction, and as the spring is attached here, the force which is responsible for the spring will act in the counterclockwise direction, and there is going to be a torque friction, which is the system friction, which we'll consider it experimental calculation. So this equation can be seen from the model. Then we'll move to the control strategy. With the control strategy, we need to understand that we have to first get the spring model, which we are using over here. So this spring model, the spring constant has to be calculated. This will be a basic system where a spring is hung from the system, and the second end, open end of the spring is attached to some of the weights, and then the spring constant is calculated. So we have this spring model, and then joint friction is also calculated experimentally. Once that is resolved, then it is put into the system, including the muscle model, which we have developed earlier in the dynamics part. And that part is given to the, so that part is ready in the system. And how it starts is that the camera is so in our system, or in our acquisition device, we are looking at the camera, and the camera is looking at the system, and we are giving some desired position to go for one joint. So this system is for one joint. So that QD is the desired angle. And to get the desired angle, we have experimentally put KP, KD, KI values, and that is attached to this muscle model, which is given to the pressure regulator. So ultimately, what we need to do is to give pressure to the pneumatic actuator, the desired pressure, so that it goes to the desired angle, or there has to be, so basically it has to give to the desired pressure so that it has a desired compression or contraction, and which leads to the desired angle. So in the pressure regulator, which is shown in the next slide, so so the pressure regulator, desired pressure is given, and then that desired pressure is given to the robot joint. So what happens in the pressure regulator is that we have these two valves, inlet and outlet valves. So once we have a desired pressure, we give particular duty cycle till so this with this MPWM is the modified PWM, which we have shown that which is given to both inlet and outlet valves. So these control signals are given both to the inlet and outlet valves in form of duty cycle. So the valve will be on till it is activated, or the valve is open, and which let the muscle contract, and in the end gives the desired pressure, or in the end gives the desired angle. Going to the results, uh, uh, considering we have understood that we have modeled the pneumatic muscle, and the interesting observation here was that after 3 bar, which is this is the 3 bar. So after 3 bar, we can see a uh, linear force and contraction relationship, which is going to be helpful to implement a linear controller model. So with the given contraction, we can expect a desired force, or in the end desired angle. And this is the experiment we conducted. So we have given some joint angle to the system, and this is the reference point. So this is a set point control results which we have obtained. So the average response time to rise from 10 percentage to 90 percentage of a steady state response is 5.61 seconds, and the maximum overshoot of 6.87 was observed at a step amplitude of 12%. and it is in a preset tolerance range of 5%.
Hello, Nandini. You are left with around 1 minute. So, okay, you are already on conclusion slide.
Yes. Okay, so I would like to conclude that the design of our robotic arm is novel, and the control method establishes 1 degree. From the earlier slides, we understand that the control method establishes that 1 degree of freedom and 2 degree of freedom pneumatic arms can be stabilized using these linear feedback controllers. Some of the performance limiting factor which we found in the system were material used for designing were somewhat responsible for uneven friction between the surfaces, and the communication between two interfaces of code was I in a serial manner I we felt that was somewhat responsible for the delay in the execution. Thank you, everyone.
Any questions? I think there are in the question answer box. There is no question as such. So in that case, I'll ask a couple of questions, Nandini. Uh,
Okay.
so in your slide number 6, figure 2, so you have mentioned something on using binary valves. So using those binary valves, how can you control the position intermediate, like any intermediate position? Because these walls might take the starting and ending position. So within using two walls, such walls, maybe you can looks like you can four such positions you can accommodate. So what about the intermediate control at any intermediate point?
So about this, how this inlet and
Yeah.
outlet valve is controlling the like
No,
helpful
no.
in.
I'm saying this valve can you control at intermediate position, or it's only at the minimum and maximum position? It's because you mentioned it's a binary valve.
Okay. I understand. So yes, so it is able to control in the at the intermediate position. So whatever desired position we want to achieve within the workspace of the robot. So if that is what we want to achieve, so if both of the links work together, then intermediate position can be considered, and additionally uh, we give that much of pressure, or you can say release that much of air into the system, so that it contracts at so that it does not contract completely, but a certain contraction is achieved, which is responsible for the desired position or desired angle.
Okay. So can you go to this controller where the control strategy has been shown? I think slide number 13 or 14, something.
Okay.
Yeah. So over there, can you mention what's the use of this integral gain or the derivative gain? So like if we remove the integral gain from the controller, what's the effect on the set point plot? What you have mentioned in the last slide.
Okay, so when we were trying to use so we started with this just a proportional gain, and we observed that we were getting too much of overshoot, and it was not going to the reference position, so it was not coming back when it was overshooting. It was maintaining that overshoot. So we use the steady state, so we use the this integral part of the system to achieve lesser error between the reference and the actual.
Okay. So again, I will invite any of the uh, audience. If you have any questions, please feel free to ask. Still, we have 1 or 2 minutes. And go back to the slide number 11 again.
Okay.
So is it yeah? So is it like you have mentioned pressure regulator? So like in the control strategy, does it take into account regulation problem or a tracking problem? Can you explain this?
It is doing the regulation problem tracking of tracking. So it is currently able to achieve just the set point control. So uh, if the desired position is given, it reaches to the desired position. But the path, that is the tracking, that this path has to be followed, that was not achieved in this system.
Okay. Okay, Nandini, thanks a lot for your presentation.
Thank
So,
you.
so again, so there is no question, so we'll wind up.
Thank you,
So,
everyone.
thank you. So let's move to the next paper. Its paper ID is 103, Amisha Bhaskar, and the paper title is Marvel, a high pitch angle bicopter wall climbing robot. So Amisha, over to you.
Yes. Hello, I'm
Yes, Amisha, your voice is not.
Echo. Can you please be loud?
okay. Am I audible now?
Yes.
Greetings, everyone. My name is Amisha Bhaskar, a third-year undergrad student pursuing manufacturing process and automation engineering at Netaji Subhas Institute of Technology. I'm here to present my paper, a high-pitch agile bicopter wall climbing robot we named as Marvel, co-authored by Gaurav Verma and Satvik Sharma. The field of robotics has seen exponential advancement over the past few decades. Not only in industries, but robots are also now being used in sectors like defense, home care, etc. By making use of their vertical maneuverability and dexterity, wall climbing robots can be used for a variety of applications like cleaning walls, glass windows of high-rise buildings, as well as in stealth operation during search and rescue. For climbing robots, developing an adhesion mechanism that reliably clings onto the surface without separation is one of the most challenging problems among all due to the variability in surface materials and topology. Popular adhesive mechanisms include magnetic adhesion using permanent magnets or electromagnetics, vacuum suction mechanism using suction cups for movement, and bio-inspired climbing mechanism on material based upon animal locomotion. The first technique for wall climbing robot is done by vacuum suction cups developed by Panish and Chen. The limitation of suction-based robot is that suction cups are required perfect sealing suction chamber. It can move in slow speed because it requires climbing mechanisms and materials. Robot using permanent magnet or electromagnets were developed by Greco, Shen, and Howalder. These robots are simple but good enough for steel walls. However, their applications are limited due to nature of magnets. Previous works on climbing robots show that particular solution cannot efficiently handle varying surface materials and topology. Current approaches can handle only a handful of such scenarios, exception being the single propeller climbing robot. Propeller type wall climbing robots were developed by Nishi and Disney Research. It consumes power even when clung to the surface. One disadvantage with a single propeller type wall climbing robot is high amount of jerk generated during ground to wall transition. Here are some references to the literature review presented in the previous slide. Moving on to the objective and motivation behind our problem statement, we wanted to design a robot which is capable of flying, driving, and climbing up the walls. Designing the wall climbing mechanism independent of surface topologies. We wanted it to enable smooth floor to wall transition and vice versa. To define a relationship between 6 degree of freedom system with angular velocity, attitude of robot, and dual axis tilting angles of the propellers. And the motivation behind creating such robot is for applications in cleaning of high-rise buildings, surveillance, etc. Surface independent climbing mechanism increases the adaptability and robustness of the robot. The paper proposes a robot that can climb any topology with single airframe. This slide shows the wall climbing bicopter with dual axis servo control tilting propellers. Here you can see there are two propellers, two servo motors, which are tilting these propellers in x-axis. In the same way, we have used two servo motors here, which are tilting the propellers with respect to y-axis. The major factor considered in this work are the position of center of mass and propellers and wheels. The center of mass of robot is kept close to the wall surface to rescue the movement due to gravity on the robot, hence making the design more energy efficient, more stable, and easier to control. The propellers are placed marginally offset from the geometric center of the robot to reduce the chances of toppling. The wheels are positioned strategically to minimize the contact area of the wheels and surface. The whole system was designed within a weight limit of 800 grams without compromising on the rigidity and stability of the mechanical structure. The reduced weight enhanced the operational time and hence reachable workspace of the robot too. Propeller-type wall climbing robot requires thrust that is generated from the propeller in the rotor system to hold and move itself on the interested climbing surfaces. Blade element theory is applied to the blade to obtain better aerodynamics. Initially, when the blade is rotating at a constant angular velocity, a small section of blade is considered for force analysis. Then, integration is performed over the propeller radius to get overall thrust, torque, and performance analysis of propeller. The aerodynamic of the rotor system is considered using Bernoulli's equation for energy and moment conservation. Figure shows free body diagram of the sectioning blade where you can see V0 denote axial flow at propeller disc, V1 denotes section local flow velocity vector, V2 denotes angular flow velocity vector, theta is the geometric pitch angle that you can see from here, alpha is the angle of attack for blade section. Using blade section properties, we obtain blade element thrust and torque for n number of blades, which can be seen from the equation here where rho and c are the air density and blade chord respectively. Psi is the difference in angle between thrust and lift vector. CA and CD are the lift coefficient and drag coefficient respectively, and whereas the R is the propeller radius. Now this figure shows a free body diagram of the proposed wall climbing robot. Here, three references are used, labeled as frame 1, frame 2, and frame 3. That you can see from here. Frame 1 or F1 is the wall frame. Frame 2 or F2 is fixed at the gravity of the robot, which is here. Frame 3 or F3 is defined and fixed at each rotor. That you can see these places. Now we are about to explain the coordinate system of the robot that we have shown earlier. Each rotor of the robot is assigned a reference frame in order to obtain its kinematic and dynamic equation. The rotor's reference frame axes are aligned with the global reference frame in a way such that there is 180-degree rotational transformation about z-axis in counterclockwise direction. This transformation for each rotor is shown in the equation here. Since F3 is fixed to the rotor, equations are translated from F3 to F2 for further calculations. As a result of translating the local axis of each rotor with reference to F2, three matrices for each rotation of each axis are obtained are Rx, Ry, and Rz. As you can see from here, these delta I and gamma I are the tilting angle along x-axis and y-axis respectively. And I is 1 and 2, which is propeller 1 and propeller 2. Now the rotation matrix is comprised of dual axis tilting angle, which transforms the thrust vector into force vector applied to the center of gravity, which can be shown from the equation here, where I is 1 and 2 and delta I and gamma I, as I have explained earlier, are the tilting angles of each propeller along x and y axis. The rotation matrix from the body F2 to F3, F1 fixed frame is R to 1, which is shown from this equation here. Coming to the force equations that we have applied on here, for the calculation of angular acceleration, general kinematic equation for the bicopter has been implemented. The speed of each rotor is being represented by omega I. The total or net force acting on the robot Ft is the sum of propulsive force Fp and gravitational force Fg. Each rotor generates a propulsive force, which you can see from here, where Ti is the thrust, Ki omega square, and Ki is the thrust coefficient for each propellers. Now, each rotor generates a propulsive force along z-axis in the rotor frame. Therefore, net propulsive force is the vector sum of the forces generated by both the rotors. This equation shows the components of propulsive force in x, y, and z direction, where T1 and T2 are the thrusts, whereas mu and eta are the coefficient of force dynamic along x, y, and z axis. I have explained and derived this mu naught and eta in my paper. So if you want further information on that, you can refer to my paper. Here is the torque equation. Spinning propeller result in two types of torque, which is reactive and drag. In this system, we have two rotors attached to two identical rings, and the total torque for each individual rotor can be expressed in the body coordinate as shown in this equation, where LP, one second, sorry, where LP is shown here, Rx and Ry as shown in the previous slides, the rotation matrices multiplied with distance 0, 0. This is the distance between center of mass of the robot and rotor. Drag torque opposes the rotation of torque, which is a result of aerodynamic drag force on the rotor. The ith propeller approximated drag torque expressed in tau d, which is here, where Rx and Ry is similarly as explained earlier in the previous slide. And this Qi is the torque coefficient, which is negative for propeller rotating clockwise and positive for counterclockwise rotating propellers. The component of torque in x, y, and z direction can be shown in the figure here. Again, IPX, IPY, IPZ are the inertia component of propeller along x, y, z axis. If you want further description of these terms, I have explained it in my paper. You can refer my paper for further information. Now coming to the force-torque combined equation mixer. According to Newton-Euler method, the force and torque with respect to bicopter body frame are expressed in the form of matrix, where V is the body velocity vector, which is a component along the each axis represented as Vx, Vy, and Vz. Omega is the body angular velocity vector. M specifies the mass of the robot. I is the diagonal, Ixx, Iyy, Izz is the inertia matrix in body coordinate frame. The second term in the equation for Ft represents the Coriolis force. Ft includes lift and drag forces generated by propeller and gravity force. Tau includes gyroscopic moments, propeller torques, thrust vectoring. Here you can see the control system architecture where multiple daisy chain proportional controllers are used on various state parameters such as velocity, angular acceleration, etc. to ensure that the robot follows desired trajectory in both the scenarios that I'll be explaining in these two slides. In this figure, RPY represents roll pitch yaw separately. The same control system is used on all the three variables. The commands sent with respect to inertial world, frame 1, are represented by RPY command and velocity command, V command. The 6 equations are used to calculate 6 unknown. Principal branch of inverse trigonometric function is being used to respect the hardware limits. The gravity term is included in the feedback path, hence has not been included in the equation for the mixer as expressed in these equations. Coming to the result, as the operation verification for the robot, basic flying operations were performed, such as horizontal movement with any desired tilt angle in the air to stick to the wall, and a bot which was operated to climb on the wall from the ground, which is this scenario that I'll be explaining now. First, I'll show you the video. Yeah, this is the video for wall climbing. You can see the smooth ground to wall transition, and yeah, I'll explain it here. Okay, so I've taken screenshots of a particular movement where the changes can be seen with respect to tilting angles, like major changes. So firstly, here you can see both these propellers are tilted at slightly tilted and in the same direction. Then when it goes there in the corner where there is ground to wall transition, both these propellers are tilted in opposite direction for smooth transitioning of wall. Now here, when the robot is on the wall, again, both these propellers are in same direction, but tilted a little bit more than these grounds because it needs more thrust here. Again, when here the tilting is required in another direction, one propeller has been tilted with respect to x-axis to provide tiltation here. And also we have used a steering mechanism which could help with these tilting.
Hello, Amisha. You are left with 1 more minute to wind up.
Just one slide is there to
Yeah,
explain.
it's okay. Yeah.
Okay. So another scenario is this one. I'll show you the video of this one too. 1 second. This is a scenario where there is a horizontal movement in the air and it sticks to the wall. Okay. Okay, so verification of these proposed dynamic model, PID control for yaw, pitch and roll and tilting angles, MATLAB and PyBullet softwares are used. The wheels move freely in the direction of the motion produced by the propellers. The tilting angles y-axis are denoted by gamma 1 and gamma 2 and delta 1 and delta 2 as the tilting angles along axes of the propeller frame. Now, in the previous scenario that you can see at t is equal to 15 second, it had this transition from ground to wall, and therefore there was these opposite direction in the tilting axis were experienced, and there was a in the same manner here in this slide you can see at t is equal to 10 second and till t is equal to 20 second there is a gradual change in tilting angles which helps in high pitch agility. Then we come to conclusion, where we conclude that we have designed a robot which is capable of flying, driving, and climbing up the walls. Designed a wall mechanism independent of the surface topologies and enabled smooth flow to wall transition. We also presented the double propeller type wall climbing robot whose rotors can be dynamically actuated, and dynamic model and attitude control based on nested PID control method has been presented. Two scenarios which I have explained earlier in previous slides were simulated to verify the dynamic model. The attitude stabilizing controller is constructed according to the PID controller parameters, and the motion response is verified using simulation. At the same time, the flight simulation also show that the attitude control algorithm can effectively...
It's okay. I think we are short of time now. Let's keep some time for question and answers.
Sure, sir.
So thank you, Misha. Your first question is the system understudy is under-actuated. So that's the first question we have received. Is the system understudy is under-actuated?
Can you repeat the question? How where is the question?
I'm reading it out for you. Is the system under study is under-actuated?
Yes, sir. This system is under-actuated.
So can you mention like how many degrees of freedom?
This is an actuated system where at a particular point where we use this ground to wall transition or tilting angles, when we do this some transition stuff, then all the actuators are actuated at that particular point dynamically. So
like can you mention like how many degrees of freedom are initially, and when this transition takes place, so how many degrees are reduced and why they need to be reduced?
So when the transition takes place, 1 second, I'll present my slide again. Sorry. Here, when there is a transition, then all the joints are actuated at the same time. So this can be called as an actuated system at that particular point. This point where these scenario 3 where we just need to tilt these angles at a particular like x-axis and not the y-axis tiltation is required, then 1 degree of freedom is reduced at that particular point.
Okay, so the next question is from Ranjan Dasgupta. So how are tilt angles being controlled?
Tilting angles have been controlled using PID.
So like what's the, you can say, how do you design the PID controller? What's the control objective in that case? Can you show some control law or how the PID controller will work, or how can we design this PID controller for tilt angle control?
I've cited a reference in my paper where this tilting angle controllers has been performed. So I can show you, you can refer to my paper and the references has been there where this control system has been explained.
Maybe you can just give a brief, what do you mean by how can we design this such kind of controller, PID controller? So like we have 3 parameters, how to tune those parameters and what kind of control objective you have taken into account to make such complicated controller?
So here we have simplified it, like this one where we have used three PID controllers with these DAisy controllers, where these pitch are only controlled, and below that this is velocity and angular accelerations are controlled with these things.
Amisha, you are saying you are used multiple PID controllers, so that will be even more complicated. So you are saying how to use one single PID controller. What is the control objective? Okay, no problem. Next question is, how have you done any kind of stability analysis?
Stability analysis, yeah, I mean, we have performed stability analysis in our mechanical stability has been analyzed in SolidWorks using static and
There
different
is like
equations.
in the control jargon, there is a proper, like you have to write a number of equations and verify those equations from the stability point of view, because this your system is unstable, and the stability is one of the prime issue. So how do you ensure the stability of your robot?
So we have been tracking these position tracking errors, and using those we are stabilizing it. I mean, these
Okay.
PID, in future we are planning to involve this inverse dynamic. No, in future we are planning to involve this adaptive robust time delay control, which would help in stability analysis for our. I mean, which would greatly impact the stability for this model when we are implementing it on hardware.
Okay, so there are one or two more questions. So let's quickly take up. The video shown is a simulation or actual robot flying.
This one is simulation, sir, on PyBullet.
Okay, so are you planning to show this experimental also in future, or?
Yes, sir. We are planning on. I mean, the hardware was ready, but because of COVID situation,
Okay,
we were
that's okay.
not allowed to
And last
go
question,
outside.
I will just take up one more question. What's the difference between the popular ETH Zurich Disney wall climbing robot with the and your robot?
Uh, that robot cannot fly, and it cannot. It has a reduced degree of freedom than ours. In the air, it can fly. It can pitch itself completely, and it can go in the narrow spaces too. But in Disney Research one, we cannot do that.
Okay, okay, Amisha, thanks a lot for your presentation. And keep doing your work, and maybe you can show even experimental works also in your future
Sure, sir.
presentation. Okay, thanks. So
Thank you.
let's go to the next paper. So the next paper ID is 110, Chinmay Samak, and the title of the paper is Proximally Optimal Predictive Control Algorithm for Path Tracking of Self-Driving Cars. So Chinmay, are you ready?
I hope my screen is visible and I am audible.
Yes, Chinmay, you are audible and screen is visible also.
Okay, so good afternoon, everyone. I am here to present our recent work on proximity optimal predictive control algorithm for path tracking of self-driving cars. The key motivation behind this research was to come up with a control algorithm that can mitigate or bridge the gap between the simplistic error-driven controllers and optimal control strategies, and ensure effective path tracking of self-driving cars in real time. So coming to the research objectives, the first and foremost objective was to lay the foundation of the work by studying the established control algorithms which form the state of the art in the field. The next objective was to perform critical analysis of different corner cases and limitations of the state of the art. And based on the analyzed limitations or corner cases, come up with a better controller design for lateral as well as longitudinal dynamics of the vehicle. The final objective was to perform exhaustive experimentation in terms of dynamic simulation tests and present a comparative analysis of what we are proposing in this work against the state of the art. Coming to the literature review, the first and foremost control method that comes to mind in terms of trajectory tracking is obviously a simple PID controller. Now, although it has various advantages such as simplicity, the primary disadvantage of this method is that it operates only it functions well only around the operating point for which the controller was tuned, and therefore it is not a very robust technique. Gain scheduling methods can be used and they can be thought of as a way to mitigate this problem, but again, it is not a very good idea to do that, and it also adds to the complexity of the control design, as well as you cannot really schedule gains for each and every dynamic situation that the vehicle is expected to encounter. Coming to the next state of the art, which is the pure pursuit control algorithm. This is a geometric path tracking algorithm, and it operates on the cross track error with respect to the reference trajectory and the vehicle pose. It uses a look ahead point on the reference trajectory, and the vehicle is technically in pursuit of that point. So, if we consider this formulation of the pure pursuit controller, we can clearly observe that the heading error of the vehicle is not at all considered here. Secondly, it assumes the availability of this look ahead point, which means that towards the end of the reference trajectory, if suppose this point what I'm showing here is the end of the reference trajectory, there is technically no look ahead point available or defined. So in that case, the controller can generate highly erratic commands, which is not at all desired. The third state of the art method is of Stanley controller, which was primarily designed to mitigate the drawbacks associated with the pure pursuit algorithm. Here we can see that the control algorithm is considering both heading as well as cross-track errors. However, there is a lack of clear geometric formulation in this case. Particularly speaking, the inverse tangent function used for, in the control law is, as what authors state, is just to minimize the overshoot in the control commands, and it does not form any geometric formulation with respect to the vehicle geometry and the reference trajectory. Secondly, it is a highly reactive or sluggish controller since it uses a closest point on the reference trajectory as opposed to a look ahead point. Now, if we consider that the initial cross-track error is high, then the vehicle is bound to move very suddenly towards the reference trajectory due to the highly erratic control commands generated by the controller. But this is not at all desired, so the authors propose softening coefficient in the denominator. But again, if we are to tune this controller for smooth maneuvers, then the controller behaves in a highly sluggish manner in under highly dynamic conditions. Finally, coming to the optimal control strategies, we are all aware of the model predictive controller. The key complexity in the design of this controller is that the control engineer has to come up with the cost function as well as the constraints that are to be fed to the optimizer to solve a constraint optimization problem. The weight assignment of each of the element associated with the cost function is another challenge, wherein the different elements can be competing and which might lead to corner cases and limitations. Finally, the prediction and control horizons are also to be perfectly tuned for getting the most out of this control law. Apart from these type of design complexities, the fundamental reason of limited use of this algorithm or the control strategy is the complexity involved in terms of computational burden. And if we see the structure of this controller, which has to numerically optimize the cost function given the weights and constraints and the plant model to come up with the control commands at each time step, predict the behavior of the model up to a certain prediction horizon, and then in a receding horizon manner apply control inputs to the vehicle, then all of this for an onboard computer to compute in real time becomes very difficult. So in order to mitigate all these limiting factors and challenges associated with the state of the art, we have come up with a control law that can potentially minimize these. So for the simulation, we have used Carla simulator, which offers a realistic dynamic simulation. And we fixed the simulation time step to 50 milliseconds to avoid any effects of the changes due to the computation of the due to environment. So we selected the race track for the simulation, which consists of different maneuvers like straight stretches as well as curved roads, and requiring different velocity profiles at different time instants. For vehicle representation, we are using a kinematic bicycle model as denoted here. However, it is not at all necessary or a strict requirement for the control algorithm that we are presenting. For the vehicle, we are assuming that the vehicle coordinate system is attached to the front axle of the vehicle as shown here. Coming to the trajectory representation, the trajectory is defined with respect to the global coordinate system, which is originally a spline tracing the center of the track, and which has been sliced into 1,274 waypoints with approximately 1 meter resolution between each waypoint. And then as the vehicle proceeds in the near neighborhood of the vehicle's current pose, we are again interpolating the waypoints with a higher resolution of 1 centimeter on line. Coming to the lateral and longitudinal control design, first I will speak about the lateral controller, which is the proximally optimal predictive control algorithm. So first we initialize a list of steering commands in the near neighborhood of the current previous one, and then we compute a look ahead distance based on the threshold value and the current speed of the vehicle to give it an adaptive nature. Based on the computed look ahead point and the current vehicle's position, we then compute a look ahead point index using this particular set of equation, which basically means that if there is a waypoint available in the waypoint list that lies in the threshold value epsilon of the current vehicle pose, then we return that. Else, we just return the last waypoint to avoid instability. Uh, then based on the index obtained through this equation, we just return the actual coordinates of the waypoint. Then we initialize the optimization parameters and enter the lightweight optimization loop. In the loop, for each of the element in the control command list, we first predict the vehicle location based on the current states and the particular element in the list using the state transition equation as shown here, wherein we are particularly interested in the x and y coordinates. And based on the predicted location, we compute the distance between this location of the vehicle and the look ahead point that we had earlier. And we return this control command that minimizes the distance between the predicted vehicle location and the actual look ahead point that is on the reference trajectory. This way, we can theoretically guarantee that the trajectory tracking is going to be in an optimal way, where we try to minimize the distance between the predicted vehicle pose and the look ahead point. Coming to the longitudinal controller design, this is a coupled control law wherein the longitudinal controller is influenced by the lateral controller, and the steering command written by the lateral controller is fed along with the limits for velocity as well as the steering. And a cutoff constant is introduced to first of all offset to give an offset to avoid any dead zone that is present in the vehicle due to changes in elevation, for example, and to limit the aggressiveness of the controller as well. Coming to the results, here I will be demonstrating this dynamic simulation test for the different controllers. Firstly, coming to the PID controller, as you can see in the simulation, on the left hand side we have the vehicle state, and on the right hand side we can see the trajectory. The key thing to note in case of PID controller is that it is overshooting initially to above 50 degrees in terms of steering angle, and even in the further instances of the simulation, you can see that there is a high fluctuation in the steering command, although the trajectory tracking looks fine. Now, since the throttle controller is adaptive in by the lateral control, you can see that the velocity is as well affected due to this performance. Coming to the pure pursuit control algorithm, if you recall, I stated that the drawback of this method is during the end phases, wherein the look ahead point suddenly vanishes. Now, to avoid that kind of instability, we actually kept feeding the last waypoint to the controller. However, obviously that is not the best solution. Another thing to note here is that when the control command is in the neighborhood of 0, the controller is providing a kind of fluctuating control command for the vehicle. However, since there is a smooth transition in control commands, you can observe that the velocity is not affected very much here. Now, if you the Stanley control law, the initial part of the simulation itself shows that the controller has generated erratic commands due to its highly reactive nature. There is no other significant drawback of this controller, as I said. However, if we had to, avoid this kind of situation, we would have to tune it for a smoother response. Then it would have underperformed in the rest of the trajectory where there are sharp turns at a higher velocity. again, as you can observe, the fluctuation is not very much, so the velocity is not affected that much. Now, coming to the proximally optimal predictive control algorithm that we are proposing in this work, you can clearly observe the smooth actuation as well as the range in which it is overshooting initially. Now, if you observe that all the controllers are overshooting initially, that is because the vehicle is spawned towards the left of the lane, and as I discussed earlier, the reference trajectory is through the center of the track. So that is why it overshoots initially. But if you see there is a minimal overshoot in case of the proximally optimal predictive control algorithm that we are proposing, and as a result, the velocity profile also, if you observe, it's pretty smooth. Coming to the tracking metrics, all the results here are indicated in the mean absolute error terms. So for cross-track error and heading error, if we observe, for PID controller, the cross-track error was maximum, and for pure pursuit algorithm, the heading error was maximum. This is likely to happen since the controller does not, care about the heading error at all. Coming to the controller that we are proposing in this work, you can clearly observe that there is a minimum of cross-track as well as heading errors for the control strategy. Coming to the latency, we have implemented the entire control algorithm in Python, and which is an interpreted language. So obviously the values that you can see here are already high.
Chinmay, sorry to interrupt you. You are left with 1 more minute to conclude.
Yes, sure. Since we had the simulation engine as well as the trajectory pre-processing pipeline and the lateral and longitudinal controllers running in a single machine, the latency came out to be around 3.2 milliseconds, which roughly translates to a control loop of over 300 hertz. And this is a very much real-time execution. In conclusion, I would like to say that we have formulated and presented an efficient path tracking algorithm, which has an adaptive look ahead and a predictive nature similar to model predictive controllers. And it performs proximal optimization of the control commands, which ensures the actuation smoothing. Finally, it has a 2D coupled control law or mechanism wherein the longitudinal controllers can be of any variation. For example, here we are proposing adaptive throttle controller, which was introduced in one of our earlier works. But simple PID controllers or any type of control algorithms as well can be used. Coming to the experimental validation of this approach, we performed a series of dynamical simulation tests, and the comparative analysis has revealed evidently, as you can observe, that the path tracking of the vehicle was highly efficient and in real time with minimum cross-track and heading errors in the case of the control algorithm that we have proposed. So thank you. If you have any questions, I would be happy to answer them.
So any questions from audience side? So in the meantime, I request audience to type any question if you are having. So in the meantime, Chinmay, can you go to slide number 8? Can you make it full screen? So over here, if we see that matrix, have you if you see the first 3 rows of the B matrix, which are multiplied by UT and U delta. So all 3 are 0, which means that the control input has no effect on those particular states, whereas the 4th and 5th state are decoupled. So if you see the first bigger matrix, 4th row and 5th row, so they are entirely decoupled from the first 3 states. So have you ensured the controllability of this system? So whether this matrix or the controller is controllable or the plant is controllable, because if you see carefully, the first 3 states all are 0, first 3 rows, and so which means the control input has no effect on the states, and the remaining 2 states, the bottom 2, are totally decoupled. So can you comment on this?
Yes, sir. Actually, they are not like, as you can see, they are if you see observe this particular part of the equation, then as you said, you are absolutely correct. But these are influencing the velocity at linear and angular velocity terms, which are affecting the states of the future states. For example, if you can see the delta t terms in this
they are not affecting, because if you see the 4th and 5th row, so these 2 states are decoupled from rest of the states. If you see only the 4th row and 5th row, So V depends only on Vi plus 1 depends only on Vi, and omega I plus 1 depends only on omega I. So from the fourth and fifth state, it is like, according to me, looks like these are decoupled states. So how these states will affect the other states? Are you getting my question?
Not exactly.
So if you see the fourth row,
These, you mean these two, right?
no, the earlier matrix, the bigger matrix.
This one.
So it's having 3 0 entries. It's only the diagonal on your, you are having 1. So 0 0 0 1 0, right? So
Yeah,
which
okay,
means
this row.
Vi plus 1 depends only on Vi.
Yes, sir.
So which means it's a decoupled state which does not going to affect the any other state.
No, sir. If you see that, if you consider closely that this delta t and delta t terms on the matrix multiplication, this Vt will be affecting the x and y, and
Okay.
for omega also it will be affecting the theta at the next instant.
So okay, and have you done the controllability analysis of this system?
If you mean like complete like theoretical analysis of the controllability, uh, then we have not done it actually, but
Okay.
since as I stated in the earlier part of the presentation as well, this is just a simple kinematic bicycle model, and it's not necessary that this particular state transition equation is supposed to be fed. It can be any particular transition equation that helps you predict the future state of the vehicle.
Okay. So the next question is from Anubhav. Can you say something about the number and kind of factors considered for the vehicle dynamics, or is it automatically handled by the software you have discussed?
Yes, Carla is a simulation engine or simulator rather, which runs on the Unreal game engine, and the physics of the back like of the environment as well as the vehicle are taken care in the simulator itself. We are not modeling it here. Uh, I would just like to make a hint here that although we are using a kinematic equation for future prediction of the states, as you can see in the simulation, since it was a dynamic simulation, the model holds quite true for the nominal under nominal driving behaviors or conditions. So the physics or the dynamics has been taken care in the simulation side.
Okay. So next question is: have you checked the effect of on roll angle? Is it in acceptable bounds in simulation, as your model used for control design is a simplified 2D model?
Which angle? Sorry, I could not.
Roll angle.
Roll angle.
Have you checked the effect of roll angle?
Roll angle as in about the longitudinal axis of the vehicle.
Yeah.
What? I could not really get the question.
Okay. Let's have the next question. No problem. So any effect noticed if we choose a different time step in dynamic simulation?
There is actually no difference in the results. It was just like this time step was just fixed to ensure that due to the differences in the maybe probably due to the different computers, it should not affect the results.
Okay. So, and what about like if you change the terrain on which on the roads on which the vehicle is moving? So, what about any kind of disturbance rejection or the change of the terrain? Whether your model is controller is able to withstand that kind of real time, you can say, uncertainties?
Yes, sir. As I've also stated that under nominal driving conditions, which we have simulated, this model, this particular kinematic bicycle model holds extremely well. However, if you, as you said, under probably like racing conditions or with very wet roads under with very less coefficients of friction, then that might be required to be modeled in this particular area where we are trying to predict the future states.
So, have you done any kind of analysis on this parametric variations or disturbance rejection in the current form of your work?
Not as of now. As I said, we have currently worked only under the nominal driving conditions.
Okay, Chinmay, thanks to you. It's a very well made presentation. So, thanks once again. Let's move to the next paper.
Thank you, everyone.
So the next paper ID is 116. The speaker is Omkar Jadhav, and the title of the paper is Differential Torque Controller for Autonomous Wheeled Mobile Robots. So Omkar, over to you.
Thank you very much. In this session, I, Oka Jadhav, will be presenting on behalf of Rohit Ji and Madhu Vadati from Smart Lab IIT Gandhinagar.
Omkar, please make it full screen.
Uh, yeah.
Yeah, fine.
I'll be presenting on the differential torque controller for autonomous wheeled mobile robots. So this differential torque controller is actually inspired from a mechanical differential gearbox to drive through the surface changes during its motion. So coming to our problem statement. For a robot traveling during its motion, if one of the wheel suddenly experiences a surface change, there is an undesirable moment which is produced on the robot and which deviate because of the difference in the traction forces on the wheel. So this deviates the robot from its desired trajectory. Now, in search of the solution for this problem, we look at the commercial vehicle technology and see that the modern full-fledged differential gearbox has the solution. So we developed our torque controller based on a similar dynamics of a differential gearbox. So we demonstrate the capability of this differential torque controller using a trajectory tracking problem, along with using the proposed differential controller along with a kinematic controller. So during its literature review for developing the controller, the mobile robots are one approach of modeling the mobile robots was considering a point contact wheel model. So wheels have a point contact and it satisfies the pure rolling condition all the time. So considering this, the backstepping controllers were proposed. Input-output linearization-based controllers were also proposed. Some self-tuning adaptive control techniques were also proposed. Later in a Konduri paper, Konduri in his paper discussed the effect of wheel slip and the effect of wheel slip on the trajectory tracking and provided a technique for saturating the wheel torque for maximizing the trajectory tracking performance. However, the assumption of pure rolling condition and is not often satisfied because of the softer wheels and heavy load conditions, and the wheels have a contact patch with the ground. So for such conditions, the traction force on the wheels actually depends on the wheels slip. So therefore, the mobile robots have to be remodeled, and the control structures have been developed on such models. So for such models, the feedback linearization techniques were also used for developing the controller. Robust controllers were developed to mitigate the wheel slip. The Balakrishna and Gosal in their paper developed a controller based on the model satisfying a pure rolling condition and use that controller based to the model which has a contact path. And they showed that such controller gives good performance for the system. A similar approach has also been used in our work. Later, uh, Rajamani in his book had discussed the yaw stability control in the commercial vehicle technology, and discussed that the differential gearbox has actually the capability for the yaw stability control under the different conditions. So, coming to our modeling part, we have considered the center point A of our different mobile robot, center point A between the wheels as our tracking point. We consider its linear velocity and angular velocity as our states. So these are the kinematics given for the system. We have VR and VL are the linear velocities of our wheels. So these equations are the dynamics of the system derived from a Lagrangian using the Lagrangian approach. You can see that these are the longitudinal traction forces. F long L, F long R, and F long L are the longitudinal traction forces, which actually depends on the wheel slip ratio. So first two equations are the dynamics of our mobile robot platform, and the second two are the dynamics of our wheel dynamics. So, in order to show the trajectory tracking performance, we use a two-loop structure where the inner loop is our differential torque controller and robot dynamics. Using this inner loop, we converge the velocity errors to zero, and we have an outer loop which uses a kinematic controller and a robot kinematics, which converges the position errors to zero. So we have used the kinematic controller as referred given in this paper. You can refer to the Kanayama 1990 paper for that. So we use a differential torque control where we have derived the differential controller inspired from the mechanical gearbox. So the dynamics of the mechanical gearbox are governed by these three terms: one tau d, which is drive torque; tau t, turn torque; and q, which is a gear ratio parameter of the differential gearbox. So for simplicity, we keep the this q term as one. So considering the model of a pure rolling model satisfying the pure roll condition, we develop a model-driven PI controller for our control variables tau d and tau t. Using this control, we have the closed loop equations as this, and we can see that there are some modeling difference terms dv and d omega, which comes out because as we have developed our controller based on a model which has a pure rolling condition and have applied it on a model which has a contact path. So we further simulate this. So we initially only simulate the differential controller to see its performance. We initially we give a reference, a desired trajectory as a circle of 1 meter with a linear velocity of 1 meter per second. So that comes out to be the 1 meter step input for both the reference command PC and V omega. And during its trajectory, we are changing the surface coefficient of the left and right wheel suddenly during its trajectory. So in the second quarter, suddenly the surface coefficient, friction coefficient of right wheel is changed. In third quarter, left wheel surface friction coefficient is suddenly changed. And for this controller, we have tuned the gains manually for getting minimum overshoot and minimum settling time. So using this controller, we see these are the results during surface change and without surface change. So we see that there is a certain overshoot in the velocities. So this overshoot is because of the modeling difference terms which we were having. And we can see that using the controller during the surface changes, the controller is able to converge the velocity errors in during the surface changes. However, we see that there is the position errors. There are some position errors because of the different because of the reaction time of the differential torque control. So these are our control parameters. You can see that all the control parameters uh, tau d and tau t converges over the time. So as the velocity errors converge to zero. Now we see that the differential torque controller does its job and has converges the velocity errors. Now we want to minimize the position errors which we are having. So if we introduce the kinematic controller in this simulation case, and we can see that the position errors are driven to zero in this case, and also the velocity errors are driven to zero in this case. Similarly, we have the dive torques and turn torques. We can see that they react to the situation and make the position errors zero. So coming to the conclusion, we show that the proposed differential controller is able to handle the surface change during its trajectory and converges the velocity errors to zero. And we also show that using the cascaded control, all the position errors and the velocity errors are driven to zero. So I'd like to acknowledge IIT Gandhinagar and for giving me the resources and the divinity for giving me the ability and the power to pursue my work. And that's the end of my presentation. Thank you, and let me know if you have any.
Questions from the audience? Please do type if there are any questions. So in the meantime, Omkar, can you please tell your how you actually designed this kind of controller?
Yeah, so this was actually a model based controller.
So
We
can you tell the limitation of a model based controller?
uh, I'm not really aware with the limitations of the model based controller.
Let me give you a hint. Like model based controllers are typically used because every nonlinearity has been cut down. So the accuracy of the dynamic model is required to a great extent if we really
Yes,
want to apply.
yes.
So how do you handle this? Because there may be any lot of uncertainties in the modeling. So we are not very sure that the model we have taken into account is very close to the realistic model.
Yes.
So how
So
do you
in
take this in the model-based control?
yes, yes. So in our case as well, so we have developed the differential controller based on a model which was which was satisfying the pure ruling condition. However, we are implementing that controller to a model which has a contact patch where the traction force actually depends on slip. However, we see that the model still performs. However, we have the certain overshoot, and these overshoots can be limited by clearly choosing the gains or tuning the gains. So, yeah.
So actually, in realistic situations, over a period of time, when you keep on using a system, its parameters keep on changing, right?
Mhm.
So those parameters will not be reflected in the model which we have considered, and with the passage of time, this will reflect, and the performance of model-based controllers in such scenarios will be under question.
Yeah, yeah,
So
definitely.
have you done such kind of study that if not model-based controller, what could be the competitor or any other possible option which can work satisfactorily?
No, we haven't done that study yet. Um, However, the adaptive controllers in the literature, adaptive controllers have been used for such cases where the if the model parameters are changing, the mass is suddenly changing, then such adaptive controllers can be used for this.
So have you used any such kind of adaptive controller in your work so far?
No, sir.
Okay. And again, just as the same question, how do you tune this PID gains? So
So,
what's the effect of PIND individual parameters on the you can say physical, if we see the physical significance point of view in real time?
mhm. So in our case, if we since we have developed this controller based on a pure ruling model, so in that case there won't be any this modeling difference terms, and it will be a directly second order system. So we try to initially get a point of region of gains where we can get a desired performance, and then we have tuned those gains to get the overshoot and settling times within the region.
That's what I'm saying. Like if you remove KD from the control gain, what's the change in the results, or what's the effect on the physical system you can expect? The same thing when you once you remove KI, the integral gain. So what is the effect on the physical system in general?
So if we remove KI terms, then we will have a steady state error since there could be some different there are some disturbances on the system. So we will have a steady state errors on the system, and we won't be able to converge the velocity errors to zero.
Okay, okay, Omkar. So since there are no more questions, thank you once again
Yeah,
for your
thanks.
presentation.
Thanks.
So let's move to the next paper, next speaker. So its paper ID is 121, Udyan Banerjee, and the title of the paper is Tracking Control of a Single Link of Flexible Manipulator. So over to you, Udyan.
Yeah, thank you, sir. I would request Rajiv sir to put up Sandeep on the stage if possible for the Q&A session. Yeah, thank you. I'll be sharing my screen. So can you let me know if the screen is visible?
Yes.
Yeah, thank you. So good afternoon, everyone. I'm Udayan Banerjee. I'm a PhD scholar at Indian Institute of Technology, Delhi. And today our work focuses on the tracking control of single link flexible manipulator. So basically, uh, 3D control techniques have been well known in literature for flexible manipulators, and because of their simple structure and implementation technique. But when we have nonlinear dynamics present within the system, then we require quite high gains to achieve the same level of performance, which is almost not realizable in many cases. So in this work, we propose a modified PD controller with a feed-forward term that can achieve a tracking performance, superior tracking performance, and suppress vibration of the flexible manipulator also at reduced gains, and can also assure robustness against uncertainties. So our objectives are to, firstly, we will be showing some methods where how we come to the dynamic equations of motion using assumed mode method and well-known Denoff matrices from literature. And then we will be comparing two controllers. First is the conventional feedback PD controller on the single link flexible manipulator, and then the artificial time delay based PD controller, which is the proposed controller for this system. So basically, in literature, we have come across various techniques that have been proposed, various control techniques like optimal control technique, then feedback linearization with input shaping, impedance control techniques for trajectory tracking, position regulation for feedback for a flexible manipulator. But very few authors have looked into the angle that flexible manipulator exhibits an under-actuated behavior to design their controllers. So we would be exploiting that feature. So basically, for the modeling aspect, we initially we take up the Euler beam Bernoulli assumptions, and we consider isotropic material properties with shear stress being neglected, the shear force, and we can see that due to the UI bar deformation, the EI tilde point shifts to EI bar as shown in the figure, and the nomenclature considered is standard in the literature of flexible manipulators. So basically, we after certain calculations, we come down to the shape function that is shown here, S of x, that is considered in the model dynamics, and we consider two modes for our system, not all the 5 modes for studying the controller effect, and the values are shown in the table, one being of some 30 hertz and other of 160 hertz.
Udayan, sorry to interrupt you. I think your
Yeah.
slides are not visible here. It's a research motivation, that is, which
Okay.
I can see.
For me, it is okay, sir. I could see assumed mode method.
Okay. I
Okay.
think
So
I can
Uh,
see. Should I reconnect?
uh,
Control Shift R. You can try, sir.
Control
You will reconnect.
Shift.
so Rajiv sir, shall I wait till sir reconnects?
Yeah, you can continue. No problem. I think.
Okay. Yeah. So basically, to start from where I left, we consider the two modes, basically whose values are shown in the figure, one being of 30 hertz value, the other being of 160 hertz. So basically, in the next slide, we put up a flow chart for how the dynamic equations of motion are derived using the Dinock matrix approach from an unconstrained set of equations to a constrained set of equation using the Dinock matrices. So various matrices that are considered are shown in the equations that are quite known in the literature and can be found in the referenced paper, wherein the shape function looks like something as shown here. So basically, after simplifications, and we come down to the well-known standard equation of motion for the flexible manipulator, wherein the point to be noticed is that the torque vector that is applied is of underactuated nature, wherein only one coordinate has the actual torque, others don't have. And herein we have the unactuated part of from the vector space of R square, and we have a scalar space wherein we have the actuator coordinate. So the gravity vector, the strain energy vectors look something as shown here. So to start with, the PD control structure was inspired from the paper which is referenced here, and we basically consider the actuated coordinate and the unactuated coordinate separately, and we formulate the error for both, and we propose the controller, which is the torque expression shown here, consisting of the derivatives and the errors of the actuated coordinates as well as the unactuated coordinates. The trajectory that was considered was a sinusoidal one, whose results will be shown later on, and a null vector, as we want that we should have zero vibrations or oscillations at the tip. So the stability analysis for this part has been skipped as because of the slides constraint, but it can be easily put up using considering a suitable Lyapunov function following the paper that has been put up as reference. So coming to the proposed part, we considered the time delayed PD control. So basically the dynamics that were derived previously exhibit an underactuated behavior, and we decompose the whole system into the actuated part and the unactuated part, and we only consider the actuated subsystem dynamics, wherein the control torque, the required control torque is present. We reformulate this dynamics by adding and subtracting a positive definite matrix IA bar, which will be a design matrix, which will be shown later, and we come down to a simplified form wherein the whole dynamics is hidden inside this NA bar term. So our objective using the control will be to estimate this dynamics. The important noticeable feature is here is that the NA bar dynamics may consist of unmodeled parts or uncertainties. So how we tackle that will come to the next part. So basically, the time delayed PD control structure is shown in this red slide, the first version, and here we can see that it is inspired from the feedback linearization structure, wherein this NA bar, which was shown previously, is estimated from the previous instant data of torque as well as the acceleration, which is a model-based part, but it is estimated from the past data. And the auxiliary input part, which is quite found in literature of feedback linearization. So it is quite similar to the PD control structure that was shown before, with an added desired acceleration term. So after simplifications, we come down to control structure wherein we have a feedback part and something which is like a feed forward part. So this feedback part noticeably has reduced gains, although we used similar gains in both the structure, but when it gets multiplied with that positive definite matrix, the gain that is fed back is less, or that reflects in the actuator force is low when compared to the conventional PD controller. But the interesting part is that we have this feed forward part, which actually estimates the system dynamics and can also estimate uncertainties present within the system. Okay. So moving on to the stability analysis part, after certain calculation, we can come down to the second order error dynamics, which is shown here in this equation, wherein the zeta depends on the unactuated error coordinate and its derivative. Plus there is a sigma term which is well known in time delayed control structure literature, which is the estimation error. So ideally we would want that this estimation error should go to 0 for our convenience. So next we formulate the state vector, which is considering E and EA dot as the states, and we use this equation. So we can come down to LTI type model wherein the state is our E and EA dot, wherein A becomes the state matrix and BA is our input matrix corresponding to the zeta term. So it is well known in the LTI system literature that if we choose a positive definite matrix PA such that the Lyapunov equation is this Lyapunov equation is satisfied, and A is Hurwitz, i.e. we choose the positive definite gains here to keep A Hurwitz, and if zeta is bounded, then the errors will asymptotically converge to 0, i.e. we will get desired tracking or position control we want. So further study or details on the boundedness of this zeta term, which is quite important, that actually requires the boundedness study of this sigma term also, has been studied in this paper that has been referenced. Again, due to space constraints or slide constraint, it was not put up, and readers can refer to this paper further. So basically, coming to the results, initially we validate the model with free fall simulation, wherein we show the link angular position, the tip deflection, and the two modes along the link length with time, the variation of the two modes, of one of 30 hertz, other of 160 hertz. And the system parameters that were considered are also shown in this table. So after applying the controller, we performed two studies. One was the position control, other was the trajectory control. And we provided a step change of 60 degrees to the manipulator. And then we observed that the time delayed control shows promising results with almost a reduction of 1/4 of settling time. And moreover, we can also observe that the peak of the tip deflection is also almost 1/5 of the tip deflection that we would be getting in PD control structure. So the same effects are also observed in the sinusoidal trajectory case with the tip deflection and the trajectory tracking. So the control gains that were considered are put up here. The control gains were similar for both the structures, and the matrix is the positive definite. Here it's a scalar because our actuated coordinate is a scalar one, but for higher cases or higher spaces, we can have IA bar to be a matrix, and this is the time delay that was put up, which is basically the sampling time and to estimate the dynamics. So to conclude our work, we had put up a modified PD variant that shows promising results when it comes to transient performance as well as steady state tracking performance, and with minimizing the overshoot while in the tip deflections while controlling those coordinates also. So these were the references that were followed. Yeah, thank you. So over now, I'm open to questions.
Thank you. Then any questions from the audience? Okay. In the meantime, let me ask a couple of questions.
Yes, sir.
Then can you go to slide number 9?
Okay.
So slide number 9, EU. You are. It looks like they are crossly referred. You are referring for actuated, and EA you are referring for unactuated.
Okay. Yes. Yeah. It should be the other way. Yeah.
And the 101, the top one you have shown it as bold. Looks like it is a vector equation.
Yeah.
And the lower one is a scalar equation. I think both should be bold.
No, sir. Here the actuated coordinate is only theta, whereas unactuated has it's an r square, so it has d11 and
d1.
d12.
Kept it bold as a vector.
Yeah. Yes.
Okay. And in slide number 12, can you go to slide number 12?
Yes, sir.
So in this slide number 12, can you mention the state dynamic matrix, which you are written as AA, actuated matrix.
Yes, sir.
So this matrix you achieve with the only particular set of state variables. So this kind of structure. So
This
is there any limitation of this kind of structure
so
in
here
terms of
our states are the errors, the derivative of the error,
yeah, correct,
and
correct. Only if you take this kind of a state variable, you will get this structure of the equation
yeah,
matrix A. So is there
yes,
any limitation of this structure of matrix A? So in terms of condition number and uh, something like this.
so
So because if
let,
you see if the order of the matrix becomes very high, so
okay,
then the most of your zero null matrix zero will
yeah,
be diagonal dominant.
yes, yes.
So can you comment something on this?
Possibly, sir, that has to be looked into. That's a point we will look into that. We have not investigated that part because the modes considered here are less. Possibly, if the coordinates
So
increase,
yeah, let's for two modes it might turn out to be okay, but let's say if you have to consider higher
yeah,
modes or
okay,
higher number of links, maybe two, three, or four.
hmm,
So and the size of A becomes let's say more than 20 by 20.
okay,
So maybe in that case is that this structure you need to investigate. This
yeah,
might create some problem from the you can say condition number or stability point of view.
okay, okay.
Or if you have observed something, you can share with us also.
Not yet, sir. I will. I have noted down the point, so I will be looking into it.
And one more thing, you have mentioned something on this estimation error. So if
Yes.
you are using estimation error, are you using some kind of observer over here also?
No, sir. There is no
Or you are
observer.
estimating the state then?
Yeah, we are estimating the code dynamics using the previous past data. So that actually, if you see this equation, this model, so using this model, you can actually this NA bar, as I told, consists of the dynamics after certain simplification. So you can basically like put up an artificial delay here, and from the past torque value and the acceleration value, you can estimate this.
Okay, so it's
Yeah,
based on the previous data, not on the real time data, right?
yeah, it's the
So,
past data.
so let's say the previous data has a lot of error, and
Okay.
so how it will going to reflect the estimation of the current state?
Then the convergence has to be studied, but if it is having error, then obviously, so what sort of error you are pointing at in the
So I'm
data?
talking about the estimation error in estimating the states. So because if you're depending on the history and
Yes.
the historical data or the statistical data is not correct, so how your controller is going to take up in such scenario?
Yeah, then actually, yeah. So if so that's the next part to this, like the convergence or this estimation will not always be assured that we are perfectly estimating it. So we can add some adaptive sliding mode part to it. That will depend on the error in the controller itself, that can take care of the underestimation or overestimation that is there because of the
So
dynamics.
have you discussed about sliding mode controller over here, or are you going to consider it in your work?
Yeah, that's the next part, sir, as I told. Next
Okay.
future investigation. Yes.
Okay. So okay, then thank
Yeah.
you very much for your presentation.
There is one
Thank you, sir.
question in general chat.
Yes,
General
sir.
chat.
Yep.
Can you read, sir?
Yes, I'll do that. So, general chat here. This is the question from Sushant Maurya. Are there any chances of a resonance in the case of flexible manipulators? Is this controller preventing it somehow? Any
Yes,
kind of resonance?
we are actually trying to suppress the oscillations at the tip. So during resonance, maybe Sandeep, you can take up the question. That's what I get. Hello. Am I audible?
Yes, you are audible. Sandeep, you may have to unmute, please. Try unmuting.
Hello.
Yes, we can hear you.
Hello. Okay. Yeah, as the angular velocity of the manipulator changes, so the frequencies also changes. So there are chances of the resonance, but in our case, as we are immediately regulating to the desired position, so it's, at that location, its velocity becomes zero. So there are no chances of resonance at that location.
Okay.
Did
Okay,
I
Sandeep.
able to answer?
Yeah. I think one more question is there from Manish. What are the typical applications you are foreseeing with the flexible manipulator? With the kind of work you have shown. So, what are the typical applications which you are
Yeah.
foreseeing?
Application of the flexible manipulators are in space, medical applications. Like in space, one of the example of the
Yes.
flexible manipulator is Canadarm, which is a 3-link arm. So, and the purpose of the purpose of the flexible manipulator use is that we can reduce the weight of the system, and it have higher payload ratio, weight to payload ratio, and
Yeah. So
we can
it's a general case to the someone who questioned, and we are not application restricted here. So
yeah.
it's mostly a general dynamic. Yeah. To be honest.
Okay. Okay.
Yeah.
Thank you, Sandeep and Udayan.
Yeah.
I hope
Thank you, sir.
there are no more questions. Thank you. Thank you. So over to you again. Once again, I think Rajiv, we are left with no other paper. There are
No,
5 papers in this session.
yes, sir, we are done with all the papers in this session.
So once again, I will thank you to all the audience, all the participants, all the dignitaries for attending this session. We have 5 speakers. All have done very well. So thank you once again.
On behalf of the organizing committee, I would like to thank Professor Ashish Singla for taking out his time and chairing this session, technical session 2. Do we have Ashish Datta, sir? Okay. So the next session will start at 4 p.m. All the speakers, I'll be sharing my screen now. So they are requested to just make sure that the slides are working. The other people can take a short break and report back at 4 p.m. Do we have Rajshekhar VS? Ashish Majitia. I'm making these people. I don't see Umesh Patkar. Is there anyone from paper ID 74? If so, please raise your hand. Then we have Deep Narayan Ray for paper ID 79. Saurabh Chowdhury. There is one Saurabh. I hope it is the same Saurabh. Debhadrata. Debhadrata Sarkar. No, I don't see Debhadrata Sarkar. Paper ID 97. So we do have Rajshekhar, we have Ashish Majitia, we do have so Deep Narayan, sir, are you there? Can you please unmute?
Hello.
Yes, sir. So paper ID 74, will you be presenting?
Umesh Patkar is also there, okay?
One second.
Yeah,
Umesh.
just I will request you to also allow Abhijit Mondol, Dr. Abhijit Mondol.
Is he there here? I don't see him.
You don't see him?
Avijit Mondal. Yes.
Yes, Abhijit Mondol.
Okay, I'm adding him. And Saurabh is there. Debhadrata.
হ্যাঁ 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 ঠিক আছে তাহলে আমি আপনাকে পরে কথা বলে নিচ্ছি।
Can you please mute, please? Yeah.
ওই বুঝলি তো বল ঠিক আছে
Okay. So do we have paper ID 97? Debhadrata Sarkar, Sagni Chakraborty, Aman Arora, Soumen Sen. Anyone? Sagnik, Aman, Soumen. Okay. I think we don't have one person from there. Okay, Rajshekar, you may please try to share your screen and quickly check. Rajshekar, kindly share your screen. I don't hear you. Yeah, there are two requests. What are they? Rajshekar, we don't see your screen. No, nothing is seen. Okay, now we see something. Can you speak? We don't hear you. Are you on Google Chrome? If not, please log on from Google Chrome. Let us go to the other speakers. We'll come back to you. So the next, do we have Ashish Majitia? Please share your screen. Rajshekar, you may have to check your settings. Ashish, please.
Yes, good afternoon, sir.
Yes.
Am I audible?
Yes, we can hear you. You can go to full screen mode quickly.
Can you see full screen, sir?
No, it's not. So come back, come out of full screen and go to view mode.
One second, sir.
Rajshekar, you'll have to stop your screen now. We don't see. Okay. Yes. So now we can see. Go to the next slide. Okay, done. You may stop sharing. Next, do we have Umesh Patkar from 74 or Deep Narayan Ray from 79? We have Soumen Sen. I think Soumen Sen, sir, was one of the last paper author. I'm making him as one of the presenter. Deep Narayan Ray. Yes, we can see the screen. You may please go to the full screen mode and check whether it works. Okay, sir. It works. You may stop sharing. Saurabh Chaudhary.
Yes, sir.
Okay, you'll have to make primary. Saurabh.
Yes,
Yeah,
sir.
you'll.
Yes, sir. Yes.
Yeah, I can see the screen. Okay, done. Next, do we have last paper, Debhadrata Sarkar, or I think I added so many Sen.
Yeah, we are presenting. Visible?
Yes, sir, it is coming.
Is it visible?
One second. There is Soumen Sen. Yes, we can see. Can you go to the full screen, please? Okay, we can see. Now, please stop sharing. I think the first speaker, Rajshekar, we have some issues. Others can just be around. Another 10 minutes will start. Avijit Mandal, you also have to share. Do you have to please unmute?
Yeah, I don't have to share. Dr. Dipan Narayan Roy will be sharing. So,
okay.
Yeah.
Who is there for paper 74?
I guess Dr. Umesh Patkar.
Patkar is there.
Yeah, I'll just add him. Yeah. Okay, Dr. Umesh Patkar, kindly share your screen and try it out.
Yeah. Good afternoon, sir.
Yes, please share your screen.
Just one second. Is it okay?
Yes, kindly go to the full screen of your PowerPoint and
Rajiv, has Ekta come?
I'll just check, sir. No, I don't see her. Can you please follow up, sir?
Yeah,
Sir,
no, sure, sir.
is it okay?
Yes, we can see it. Thank you. You can stop.
Yeah.
And Rajshekhar, we have issues with your system. Please.
Hello.
Yes, Rajshekhar.
Can you hear me?
Yes.
Okay. I'll start sharing it.
1 second. We have to stop. Okay, I'll just make you primary.
Okay. So
No, I don't see your screen. Are you on Mac by any chance?
no. I'm just yet to start the session. Yeah. I'm on dual screen basically. So just coming.
Okay. Yes, we can see. Go to the next slide.
Yeah, I went.
Okay, fine. So all speakers are set. So we'll start exactly at 4 o'clock. Please be around.
मैं कैमरा को ऑफ कर दिया माइक को Alt C करना पड़ेगा
Ashish sir, you
Yeah.
could contact, or should I?
No, you have a number. I don't have a number.
Yes,
How many?
I have.
1,
All
2, 3,
6.
4, 5, 6 are there. No?
6 are there. I will just message her. Sir, could you go through the file I just sent?
No, I didn't. Just now you sent it.
Yeah, some time back. So that is similar to our book of abstract. So once you approve, I'll put it on the website. Okay, I'll have to make other old people like Amisha Bhaskar will go out of stage. Yeah, only one.
That is AIR souvenir or?
Yeah, the same one. PDF, PowerPoint, both are there.
Yeah, that's okay. Yes. Yeah, so this we can put it up. Yes.
Okay, I'll just do it once we start the session. So I messaged Ikta ma'am. She hasn't seen it yet. Maybe I'll just call her now.
So the poster presenter names also you have checked, right?
Hello.
Yes, ma'am.
Yeah. Am I audible? All fine?
Yes. Ashish sir.
Good afternoon, sir.
Good afternoon. Yeah. Rajiv, could you check the names of the poster presenters also?
I checked.
They are all correct, right?
Yes.
Okay. So Ekta, you have the format of the marks, right?
Yes, I do have. I'll try to fill side by side. Anji.
Yeah. Okay. So we can start at 3 o'clock.
4.
Sorry, 4 o'clock. So everybody gets 14 minutes for presentation and then 3 minutes for
I
questions.
think there is some audio issue at my end. Is Dr. Ashish anybody speaking? At present, I'm not able to hear.
Yes, 1, 2, 3, check. Can you hear
Oh,
me?
it's okay. It's okay. Yeah, I can.
Yeah, can you hear me?
Yes, yes.
Okay. So the presentation is for 14 minutes and we have 3 minutes for questions.
14 minutes presentation, 3 minutes questions. Ekta ma'am,
Yeah.
did you hear? Okay.
Yes, because there are 6. Okay, 3 minutes question.
Yeah.
So 18 to 19 minutes per candidate.
Hmm. Right, right, right.
So Rajiv will put this up on the website somewhere, huh?
Yes, sir, I'll do it right away.
Yeah.
And also session chairs for tomorrow, if you can inform. So I have created simpler files with marks and the abstracts. So we'll send it right away.
So tomorrow morning session 4 is Vineet.
Vineet, let me write.
Vashishta.
Okay.
Then session 5 is Mangal
Can I join
Kotari.
again? Actually, when Professor Ashish speaking, I'm not able to hear him. Or is it only between you and him?
No, he's telling me, I mean, I can hear both.
Okay, but I cannot hear both. I hope there shouldn't be any issue before in between. Anyway, I'm attending this morning, all fine. Let's hope.
Okay, Vineet is number 4. Who is number 5?
Vineet, number 5 is Mangal Kotari.
Okay, and then do we have for posters?
Posters is myself because there is nobody.
Okay, and it's a big one.
Yeah, 3 hours.
Okay. And then 7 is another poster. 3 posters.
7 is 3 posters and 1 technical talk.
Yes.
That is SK Saha.
3 posters. He has one of
And-
the papers.
It's okay, I guess.
Okay.
So,
Then 8.
8 is nobody. 8, 9, I couldn't find anybody.
Okay, what are 8 and 9?
One is biomimetic and computer vision, and the other is machine learning.
Any speaker we have? Abhishek Sarkar, is he joining?
Oh, I don't know whether has he joined? I don't think so.
No, so far he hasn't joined.
No, I don't think so.
And 9, Suril also hasn't joined yet. Okay, so we'll figure out. For tomorrow we'll do, and then day after we'll again take a call.
So tomorrow is, I have one session in the afternoon, right? That's it.
Yes, that's a long one.
Yeah.
And regarding session chair, you will be introducing?
The speaker, you mean?
Yes,
Yeah.
speaker. Okay.
For tomorrow, right?
Yes, tomorrow.
Shall I join again because I'm not able to hear Dr. Ashish. Let me join.
Ma'am, you do Control Shift R. You'll do a hard refresh. Control Shift R.
Okay.
Okay, we are almost ready. Once
Yeah.
she joins, we'll just. Rajshekhar, please be ready.
Okay.
Yes, ma'am.
Yeah.
Ashish sir, you can speak. Let her test.
Yeah, can you hear me now?
Yes.
Okay. Yeah, so we start at 4. It's already 4, so I think we can start.
Yeah, just a minute. Yes. So let us start because I can see. 1 second. I need to check participants. If all have joined.
All the speakers to turn on their webcam, we'll take one screenshot. I'll be taking so that we'll have.
Yeah, it will be better that the speakers, if they can turn on, that gives the good idea. Yes, we do have. Okay, so let us start formally. Good afternoon, everyone. And this is our session 3 for the day. And this is on the design of robotic mechanisms. We'll have 6 speakers, that is 6 papers to be taken up in this session. And our first first paper is paper ID 29. And it will be presented by Rajashekhar, VS. And the title of the paper is A Robust Aerial Gripper for Passive Grasping and Impulsive Release Using Scotch-York Mechanism. So yes, Rajashekhar, you may please share your screen, and you can take, as we have already announced, 13 to 14 minutes so that we can have good time for our question answers.
Sure. Is my screen visible and it is audible?
Yes, audible and visible both. You missed out.
Yeah. Good evening to everyone. This is VS Rajashekhar, a project associate at Indian Institute of Science, Bangalore. I'm here to present our work on passive grasping using Scotch-York mechanism, especially for aerial robots. It's specially focused for aerial robots. And we are in this presentation, I'll be focusing on the robustification process needed in the design so that the Scotch-York mechanism can be used for passive grasping and active release. In the recent days, as we know that unmanned aerial vehicles are being used for various purposes, especially for transporting objects. To accomplish this task, we need aerial grippers or manipulators which would help in grasping the object and taking it to another place and dropping it. So this initial stages where the UAVs are mounted with the object and it just goes and drops and down. But in our work, we are focusing on the UAV taking off, finding an object, coming down, picking it up, and going and placing it where it is needed. To perform this task, in this work, we are proposing a gripper design that would help in achieving this task. In most of the literature, what we find is that 1D of that is 1 degree of freedom gripper mechanisms are being used for perfect positioning of the object at the place. So in this case, 1D of grippers are enough because the vision system of the UAV is already equipped with identifying and locating the target. The gripper has to just go pick it and come. In such scenarios, 1 degree of freedom aerial grippers are more than sufficient. In this work, we propose a aerial gripper mechanism which would help in improving the endurance of the gripping system. So what I mean by improving the endurance is that the gripping mechanism takes power from the power supply which is attached to the drone. But in this case, where only active release is there, while picking up it will be passive, that is no power supply is required. Power is required for picking up. Only for dropping purpose it is required. And in the recent survey on aerial manipulation shows that 1D of grippers are actually easy to model, control, and easy to fabricate. There are two methods when it comes to using magnetic grippers because they help in attracting the object if it is coated with ferrous. In the entire this gripper is particularly focused for objects which are coated with ferrous, like maybe a sheet of ferrous on the top and the rest of the thing object can be different. So this primary purpose of focusing on this area emerged when we participated in the Mohammed bin Zayed International Robotic Challenge, which was held in Abu Dhabi in the year 2020. So for that purpose, where we had to take up bricks which could be kept on a wall to help the construction activities. So in passive grasping of objects, which is proposed in this work, it is energy efficient and increases the endurance of the UAV when compared to active grasping using electropermanent magnets. This has been experimentally proven, and it has been reported in the literature, which is on the screen. So the objective of the problem statement is that by limiting the drone size, the drone-based delivery consumes less energy per package kilometer when compared to the trucks which are conventionally used to deliver things. So this can help in for e-commerce business to develop drone technologies with groupers like this, which is proposed here, in order to actually save a lot of energy and is also economical. So the electropermanent magnets, which are commonly used, actually are not reliable, and they consume more power. The cost of the semi-permanent magnets are very high. In case of we are planning to use a semi-permanent magnet, the cost for a gripper would be very high. So also in the electropermanent magnets, they are not reliable in the sense residual magnetism is left after the it is demagnetized. That causes delay in releasing the object. So there is a need for developing a gripper which can grasp almost instantaneously and release the payload at the duration of operation at a very low cost. Hence, we have chosen a magnetic gripper with passive grasping. That is, it uses permanent magnets to grasp and releases using a Scotch-Yoke mechanism, and has which helps in achieving this task. The grippers of this kind can be used efficiently for aerial transportation. The proposed robust design stages is as follows. The proposed robust design stage starts with the gripper mechanism design or the gripper mechanism selection, and calculating the load carrying capacity of the gripper, and then optimizing the volume of the gripper, gripping like the volume which the gripper occupies below the drone, and it will be used and it would result in creating a robust aerial gripper from a design point of view. The gripper which is implemented or proposed is like follows. You can see the figure on the left where the CAT model is there, where the rotary actuator and the rotating disc, which is a part of the Scotch-Yoke mechanism, and the slider which goes slides up and down, and there are permanent magnets at the bottom which would help in attracting the ferrous-coated surfaces, and these are enclosed in a gripper mount which is attached to the drone. So the fabricated gripper is shown on the right. So you can see the gripper with the screws on the top, which can be mounted to the drone, and you can see the extreme right, the figure where there are three magnets placed at forming an equilateral triangle, which enables stability during grasp. So this deciding the side of the equilateral triangle depends on the ferrous coating which is targeted, and also on the mass of the object to be lifted. So coming to the next stage in robustification process, the gripper mechanism is actually designed, and the load carrying capacity of the gripper is to be found. So in order to do that, we calculate the maximum load carrying capacity, taking into consideration the magnetic flux density, surface area of the magnet, and the acceleration due to gravity, and the permeability of air. And using this equation, we gave the parameters which are related to our problem, and we obtained a value that the gripper can carry a maximum of 4.66 kilograms. So coming to the kinematics of the mechanism, which would actually help in optimizing the volume, this mechanism which is shown over here is a Scotch-Yoke mechanism, and it is the kinematics is done using the vector loop method, and the velocity, acceleration, and the jerk are all calculated based on the displacement equations. So coming to the dynamics of the mechanism, the Newton-Euler method is used to derive the force and momentum equations. So in this case, you can see the various links of the Scotch-Yoke mechanism being placed over here, and the Newton-Euler method was used to derive the forces and momentum in the mechanism. So the main purpose of doing the kinematic and the dynamic analysis is to create a perfect or optimized volume so that it would enable the grouper to be light in weight. So the optimization of the grouper volume, which is the next stage after calculating the load carrying capacity, and in this stage where the grouper volume is optimized, the mechanism, which is the Scotch-Yoke mechanism, is basically a planar mechanism, and the planar gripper area is to be optimized. So the objective in the optimization process is to minimize the planar area of the gripper and maximize the torque produced by the actuator. So taking these, the first thing is that is minimizing the planar area can be done using the kinematics and kinematics equations, and the maximizing the torque required to produce the produced by the actuator can be done using the dynamic equations. The constraint is the between the radius of the rotating disk and the height of the slider, which has to be 0.25 in order to meet the space restrictions below the drone. For this purpose, a multi-objective optimization weighted geometric programming technique is used. So this is used because, that is the weighted geometric programming is used because the objective functions are all polynomials, which means that the polynomial functions are those which have coefficients which are positive real numbers, and the exponentials are only real numbers. The constraint in this case is a monomial. The weighted geometric programming technique will help in deciding various things like scaling the grippers for different drones, which can be done by assigning different weights in this technique. So in another stage, in this stage, there is something called as optimizing the thickness of the disk, rotating disk in the Scotch-Yoke mechanism, which is done by using the calculating the rate and then calculating the velocity of the rotating disk from the kinematic equations, and for the force exerted during the load carrying operation. And also from these two things, we are calculating the mass of the rotating disk from the impulse equation, and using the impulse equation, this relationship, which is F average, we can find out the thickness of the disk. Since we know the density, mass, and volume, that is the planar volume we know, only the thickness of the thing is unknown, and we can find out the thickness. After doing this, we can use simple geometries and decide the shape of the enclosure, that is the gripper mount. And in the initial experiments which was done, where the gripper was mounted below the drone, as you can see in the figure on the left, it is mounted below the hexacopter, and experiments were conducted on the airfield using manual and autonomous modes. In the manual mode, you can see the bricks being lifted, that is the red brick, which is of mass 1 kg, and the green brick is of mass 1 kg but of a different dimension, and the blue brick is of mass 1.5 kg. So in the initial experiments in autonomous mode, the UAV took off in autonomous mode, did visual surveying, approached the target object, picked up the target object, and it dropped it and landed in the autonomous mode. This is done only to prove the efficiency of the gripper. So this is the video where the red brick is being picked up and dropped.
We are closing in a minute, I think. Rajashekar, just a reminder, please. Already 14 minutes, yeah.
So this is the initial testing of the green brick and also the blue brick. There was problem due to the downwash. And coming to the conclusions which we obtained for this design procedure for robustification is that we need to focus on more parameters such as downwash, which plays an important role in deciding the size of the object to be picked. This will be done in our future work along with the focus on designing a base which would pick up objects of different geometry using closed loop control. And we'll like to acknowledge the partial funding from RBCCPS IISc and the Khalifa University at Abu Dhabi, and also the team IISc TCS MBZ as a team for helping in conducting the experiments. Thank you.
Thank you. Yes, thank you to the speaker, Rajashekhar. And now some questions, please. I think I can see that there is no question mentioned in Q&A, but in chat we do have a question from Manish Chauhan. I think it is for this because it's regarding Gripper. It would be better that if we write in question and answer side so that we should not miss the questions. I can read for you, Rajashekhar. There are 2 or 3 questions. First is, what happens when the gripper is used to lift non-ferrous payload?
Okay.
Although you mentioned, but yes. Is it for non-ferrous?
No, it is only for ferrous.
Yes. What is the maximum magnetic field strength of the magnet which can be used here? Hello?
Interference capabilities of the which the drone system can handle. So it is based on that.
So in our case, we used a neodymium magnet of grade N95, which had a pulling capacity of about 4.5 kgs when done off floor, like without mounting on the drone. This magnet was able
you
to
mentioned okay, but you mentioned the payload which is required to be carried something 4.95 something. That what was that? How it is related? Have you tried to see what would be the maximum loads which it can carry? You mentioned
no, actually the load, the magnet, the 3 magnets put together can carry a maximum load of 4.5 kg when not mounted on the drone. So what we needed was up to 2 kg, which at least 50% safety factor of safety is considered, and we were able to test it up to 1.5 kg. It was able to pick up.
Okay, and from same Manish Chauhan, we have a third question. Does the use of magnet implies use of non-ferrous link mechanisms?
Exactly. The mechanisms should not be like a ferrous magnetic. Even though if it's ferrous made of ferrous materials, at least the gripping area should be like it should be like used designed properly.
Yes, because this is an important consideration. We have 1 or 2 more questions. One is from Selva Kumar. What is the payload of your drone? Although you mentioned, I think it is a similar question.
Yeah.
And what is the maximum torque produced to lift 1.5 kg? If something, then I think it will be a question regarding the actuator. If you have which actuator to be used. So what is the maximum torque produced? I think the question is required. How much required for that actuator?
Okay.
Yeah. Yeah.
So in our case, the actuator which was used had a lifting capacity of 35 kg centimeter torque, but the actual thing which we needed was in newtons for somewhere around 1.5 or something like that, roughly.
1.5 for torque you are mentioning?
Yeah, for torque.
Okay. Okay. I'm sure that such these points are given in your paper also. So anybody else who's interested in looking at the paper, because the paper, in my opinion, it has a good span. It has both theoretical as well as experimental aspects into it. So I would say that it was a good paper because the time is there for the next. So I'm not taking up any further question for this, and I congratulate you and thank you, Rajashekhar, for giving your presentation. I had 2 or 3 questions, but I'm just cutting it short. Thank you very much. Yes. Yeah. So with this, now we move to the next presentation. It is paper ID 61, and it will be presented by Ashish Majithia. And the title of the paper is Comparing the Performance of 1-phase, 2-phase, 3 and 4-phase discontinuous static gate for a quadruped robot. So yes, he has already shared. Take your 13 to 14 minutes, please. Okay.
Okay. Good afternoon, ma'am. Myself, Ashish Majithia. I am a PhD scholar at Nirma University, Gujarat. and working under the guidance of Dr. Jatin Dave sir. My domain of research is locomotion of quadruped robot. So research in quadruped robot is mainly focused on the walking algorithm, that is gait planning. And the gait of quadruped is broadly classified into static gait and dynamic gait. And in the static gait, the major research is focused on the...
Hello.
Yes. Hello. Hello.
Rajiv, is he audible to
Yes,
you?
I can hear.
Okay, I just come again. Yeah.
Control Shift R.
Yeah.
Yeah, Ashish,
Yes, sir.
Majid, yeah, you
Yes.
can go to full screen, please. Yeah, you can just start. She will be here.
Okay, so the major research in the case of static quadruped gait is focused on continuous gait, which is almost similar to the walking of animals, in which the body of the robot moves continuously throughout the locomotion cycle. And while it moves, each of the leg comes to a swing phase one after another. So in most of the time, it will be a case that the robot will be supported by the three legs, because one of the legs will be in the swing phase. But in the discontinuous gait, which is another gait, the robot moves only when all four legs are on the ground. And when the leg comes to a swing phase, robot will be steady. So because of this kind of pattern, walking pattern, discontinuous gait has some inherent advantages in terms of better stability, terrain adaptability, and energy efficiency. So here, an attempt is made to do the scientific comparison between three standard discontinuous gait, that is one phase, two phase, and four phase gaits. So some brief about the quadruped. It is one of the best trade-off between the biped and hexapod in terms of stability and control simplicity. So in the legged robot, stability is the foremost requirement, and discontinuous gaits are mathematically proven to be more stable than the continuous gait. To calculate the stability, there are some stability margins presented in different literatures, and two of them which are popular have been considered here: the static stability margin SM and longitudinal stability margin LSM. So here, this is the rectangular dark line is the robot. These four are the legs. Currently, it is in all four legs are in supporting phase. So this dotted line is the support polygon, which is having four sides. So how the SM is calculated? It is the nearest distance from CG to the support boundary, and the LSM is the nearest distance from CG to the hind or front support boundary in longitudinal direction. So that way we can calculate the stability margin. The three literatures from which these three standard gaits have been taken, one phase, two phase, and four phase, are shown over here. The objective behind this study is to formulate this three standard discontinuous gait with the same parameters, and to carry out a scientific comparison between these three gaits and prepare a guideline for suitability of particular gait in particular locomotion condition. So for which kind of terrain condition, which gait out of these three is more suitable, that kind of guideline is to be prepared. The performance parameter for this study will be the stability margin SM and LSM, and the translation of inertial frame in X, Y, and Z direction. The geometric model of the quadruped robot considered for this study is a very simple rectangular type. There are four legs, and each leg is having a rectangular workspace, which is denoted by the dotted line over here in this model. Each leg is having 3 degrees of freedom, 2 at the hip and 1 at the knee, and 2 links are there. The inertial coordinate frame is placed at the centroid of the torso. Here it is the gate diagram in which the event sequences have been shown for these three gates. So we can see that for the one phase gate, swing of all four legs happens one after another in a particular sequence. So swing of 3, then 4, then 2, and then 1, and then the body movement takes place. Similarly, in the two phase gate, swing of 4, swing of 2, then the body movement, and which is followed by swing of leg 3, 1, and then body movement. So body moves 2 times during a cycle. And here in the 4 phase gate, body moves after each of the swing. So after swing of 4, body will move, and same way it will move 4 times during a cycle. Once the gate diagram is prepared, the foot trajectory for the swing phase is decided, and a very simple rectangular trajectory is considered for the swing phase. And while robot moves forward, the foot tip is supposed to be comes backward while making the contact with the ground. So this way, this backward trajectory can be formulated. Now, once this overall swing phase and body movement phases are prepared, we need to define the position of each foot tip, each of the 4 foot tip for each particular sequence. So here for the one phase, the workspace of the leg is out of that. The 4 key points have been defined, and the position of leg 1, 2, 3, and 4. So foot tip of all 4 legs in particular different time steps, its position is mentioned over here. So from that we can do a detailed planning of the trajectory. And the leg kinematics is carried out with the DH parameter, in which we can see that theta 1, theta 2, theta 3 are the joint parameters, and L1 and L2 are the links. Based on that, the transformation matrix is prepared, and for the trajectory planning, cubic polynomial equation, a standard equation, has been used for that. So after doing this analytical study, the simulation has been carried out in the MATLAB Simulink with the package SimScape Multibody, which was demonstrated by the Dr. Dhruv from MathWorks yesterday only. So same package is used over here for the simulation of quadruped robot. First of all, the representation of robot in rigid body tree is defined. Then in order to deal with the multiple solution in inverse kinematics, the joint limits are specified, so that we can get the unique solution. So each joint is having a particular joint limit that's 0 to 90 or 0 to 180, and based on that we can get a unique inverse kinematic solution. So that is why joint limits are specified. Then the key points are defined based on the gate scheme, which was shown in last slide. Inverse kinematics is carried out with the standard function of MATLAB LM algorithm, numerical method, with these key points. And once the data of angles for those key points are obtained, trajectory planning in between them is done in the joint space. The data is fed to simulation, and simulation is run, data is acquired, and the result is compared. Here is the basic parameters of the simulation model. And here from the table, we can see that along with the effect of number of phases on the locomotion performance, one more thing is studied in this paper, that is the effect of width to length ratio of the robot torso on the locomotion performance. So 4 different values of width to length ratio of the robot torso is considered for all the 3 gates. So that way, total 12 number of simulation studies have been carried out. Here, just for the representation and some basic idea behind the simulation environment, one simulation I'm going to play. It is a one-phase discontinuous gate, and as said that swing of 4 legs happen one after another in a particular sequence, and after that body will move just once a cycle. So that way, straightforward motion of the quadruped robot can be obtained. Then the results are taken, and it is plotted for these 5 different parameters that are already stated: SM, LSM, X moment, Y moment, and Z moment. So now the plotting is done in 2 different aspects. One, to consider the effect of rho on SM or on the different parameters, and second is to observe the effect of different gate schemes, so number of phases on the parameter. So that way, for each parameter, this kind of plotting is done, and based on that, some observations are carried out. So for SM, suppose stability margin, it was observed that SM increases with the increase in rho. And as far as the gate is concerned, so 2-phase gate is having maximum value of SM, and 4-phase gate is having minimum value of SM. So this 2-phase is the most stable one among these 3 gates. And the same thing was observed with another parameter called LSM, that the 2-phase gate is having the maximum value of longitudinal stability margin. So that way we can just get the observation that the 2-phase is the most stable one, and 4-phase is the least stable one. As far as the forward displacement, so the motion in X direction, forward direction is concerned, it was observed that the value of rho, so width to length ratio, should be between 0.5 to 1 for the maximum forward displacement per locomotion cycle. And for the gate, 1-phase gate has minimum forward displacement, and 4-phase gate is having maximum forward displacement. For lateral displacement, it was observed that for all the 12 simulation studies, the maximum lateral disturbance was 0.5 millimeter, which was clearly negligible. So all the gates and all this value of rho are capable to just provide the proper longitudinal travel. In the case of fluctuation of height, so the movement in z direction, it was observed that rho doesn't have any effect on the z disturbance, but in one phase gate. So again, here from the plot we can see that these four different values of rho doesn't have any effect on this z movement of the robot. But here we can see that this yellow line is the four phase gate. It is having the minimum z movement. So minimum fluctuation in height was seen in the four phase, and maximum fluctuation in height was seen in the one phase gate. So that observation was taken once again, and based on this observation, the conclusion has been made, and a brief guideline for selection of different gate for different locomotion condition has been just listed out. So for the rough terrain, so whenever the terrain is rough, stability becomes a prior requirement, and two phase gate, which is having the maximum stability among all the discontinuous gate, and as it was stated earlier that the discontinuous gate is having the higher stability than all the continuous gates. So that is why we can say that for the rough terrain, two phase discontinuous gate is more suitable. In the case of pure flat and smooth terrain, where stability margin doesn't have a critical role, because the stability is anyway going to be maintained by keeping the CG within the support boundary. So in that condition, four phase gate is advisable to choose, because it is having maximum forward displacement per cycle, so speed will be higher. And in the condition when we need to carry a load on the robot torso, the disturbance in the height should be as low as possible, which was observed in the four phase gate. So in those conditions of carrying the load, four phase gate is a better choice. And the width to length ratio, it should be between 0.5 to 1 for getting the higher longitudinal displacement and better stability. So with this conclusion, I would like to conclude my presentation.
Okay, thank you, Ashish. And first, we have now time. We have not yet mentioned any question, but still, it has just finished in 12 minutes, so we can give more time for and wait for them to write their question. Yes. So first, yes, we have 1 second. Okay, we do have some questions. I'm just looking from where it has been started.
So the question is, in each leg, two links are in the model, but in the DH parameters, 3 theta values are there. What is the joint notation scheme of the leg? What is the maximum slope angle of the terrain?
So currently, I will just answer the second question first. We have considered the flat, smooth terrain for this study only. We have already forwarded the study for the stair environment and slope, but here we have only mentioned the flat terrain. And as far as the number of links is concerned, it is of course 2 links, but I already said that 2 joints are at hip and 1 joint is at knee. So that way it is having 3 degrees of freedom, and that is why in DH parameter we have 3 frames, but the links are only 2.
Okay. Okay, so okay, before somebody writes any another question, I would like to just know what the ratio rho, which you are also considering as the 4 values of it and showing its effect, right? So first is like, how do you just select these 4, and what is the, anyway, in the beginning, now you are concluding that 0.5 and between 0.5 to 1 is considering. So may I just know from where you have found this conclusion? Maybe I missed it, because the last conclusion which you have made for the rho value, that the ratio value, right, you have concluded that this is considered to be recommended for the design or for the fabrication. So from where this conclusion, maybe I missed that.
Yes, ma'am. So here in the case of X movement, 1 second, I will just keep it a full screen. So here it was observed that this yellow line in this 2-phase gate. So the common thing about these 3 different gates the value of rho is equal to 1 and 0.5 is having the maximum forward displacement per cycle. Though the margin is very low.
Margin is low. Yes,
Yes,
yes.
yes.
Okay. So do you think, okay, like, okay, this margin is acceptable for making, or maybe how, if I know how many times like you have repeatability of the results, are you finding it, the results, these results, what you have plotted, right, are how, for the reliability of them? So have you repeated the experiment or the simulations?
Yes, I have done 2 times, and both the time the results were same.
Okay, so let me just check for, yes, we have one more question from Sandeep Kumar. So it is what stability margin signifies?
So basically, in static gate, the CG should be within the support boundary, and the distance between the CG and the support boundary is the stability margin. So the robot is stable even though the CG is exactly on the support boundary. But whatever with the whatever value it is away from the boundary, it is a margin. So in case of any inaccuracy or in case of any error, we can get that margin. So anyway, the stability is going to be maintained. That is why the maximum stability margin is expected.
Okay, so did you mention some value for like how to get this maximum stability margin?
So calculation of this, it is
Is it
geometrically
standard?
calculated.
Okay. Okay, so yes, is there any another question? We do have time for one or two. Otherwise, we can switch to the next just to maintain time for the next. Okay, so with this, I thank you, Ashish, and congratulate you for this paper. And thank you very much. I'm sure that if somebody else will have any question, they'll write to you directly. Thank you very much. Okay, so let us move to our third presentation for the day, and it is paper ID 74, and it will be presented by Umesh Patkar, and the title is Remotely Operated Robotic System for Inspection of Cooling Water, Sump, Pump, and Intervention for Scavenging. So yes, we welcome you, Umesh, and you can now
Good afternoon, everybody.
present.
So I will share my screen. Am I audible?
Yes, yes, audible, and your screen is visible.
Yeah,
Correct.
thank you. Yeah, so first of all, let me introduce myself. Myself, Umesh Patkar. I am from CMAI Durgapur, and we are actually intervening, or we are jointly working with some of the very well-known or Navaratna companies from all over India, and NTPC is one of them. And this particularly project was done for NTPC Netra. We were joint collaborator with us also. And basically, let me give you some background. So, as all you know, these thermal power plants, they are really challenging. They really work in a very challenging environment. Whether it is a cooling power plant, or whether it is a boiler system, or whether it is a generation system, or ash handling, or maybe the fires and other things. So in this environment, if you have to work, or you have to give safety to those people. So in that way, we are working as a uh, as a uh, as a robot, or we are working. We wanted to give them robotic support or something. So in that way, we plan to jointly work with thermal power plants. So this is one of the problem where we are being interested for developing a robotic system for inspection of cooling water some. So which is an integral part of the thermal power plant. So what is very essential, as you know, on average, there are a power plant requires thousands of liters of water for the operation of power plant, and these are supplied by water bodies, reservoirs, rivers, and they normally carries the weeds, grass, and other debris, so which keep on storing in the sump of the water intake of the CW pump, that is cooling water pump. So what happens is that this actually can damage the rotor blades of the pumps and choke the flow of the water. So in the submerged part of the pump is really in the continuously in a corrosion conditions. So this happens after maybe several years or due to continuous working. So accordingly, there is a chance of sudden and unforeseen shutdown also of a power plant. So it is causing significant economic losses to the power plant. Similarly, therefore, this monitoring and inspecting of the sump, or what you can say a pump, which is submerged in the cooling water, that is in a periodical way is very vital. So presently either human divers are employed or the sump is evacuated fully for inspection. So this also takes a lot of time, as well as there is a threat. Erection of temporary structures is also required. So this causes unpredictable delays and risk. Similarly, so our aim was to develop one robotic system which will be like suited to the thermal power plants in India or NTPC like worked thermal power plants. So in this way, we have studied many some systems which are globally available. Few of them are mentioned here, like ECA High Tech by France, Robotics by Teledin Marine, as well as Genome Rove by Underwater Robotics LLC. Similarly, Deep Tracker by Deep Tracker INCs, Falcon by Subsage. So these are few commercial things available. Uh, Now, what exactly we get from all these things? So these are all used for inspection of underwater objects as well as underwater construction, repair, maintenance, survey, pipe and cable laying, monitoring, as well as driver support. So in this way, these have different weight categories, like few starting from 20 kgs to about say 1000 kgs almost. So they work at different depths also, and these requires launching dimensions also vary from few meters to about 2 meters. So all these things, they have some limitations also, like these are developed for mainly open space like sea or similar open space area, which has a limited application in a narrow space where thermal power plant or CW plant is there. So especially launching and retrieval of these robotic systems require special arrangement. Sometimes like overhead cranes and more larger openings are also required. They normally have a non-metallic frames which are very prone to damage, uh, like collision. In case of collision, this system also lack little preventive measures for against any collision also. And vision system, that is visibility in the water, that is clear sea water, may not be applicable to the water what we in a thermal power plant we get. So that is turbid. I will come to that later on also. So that and these systems, they supply power through surface stations and converters on the installed which are installed on board. So this makes the system more bulkier and heavier. So also the systems have single configuration, either they for used for inspection or they are used for only intervention. So hardly there is any interchangeability between the configurations. So let me brief out the objective or the problem statement. Here, what we have in a thermal plant is that the water through the water bodies or rivers are normally intake at the CW plant. So this is the basically what approach we normally have. This is a CW pump bay, or you can see a pipeline which carries water to the plants. And this is the opening where we can have a launch, or we can have a inspection of the CW area or sump, or what you say as a pump entry area. Uh, so here to basic objective is to develop a CW pump inspection robot for intervention capabilities subject to following changes. It should have a minimum dimension, that inspection hole for CW pump is around 600 to 600 mm. So that is roughly half a meter or maybe little more than that. And it should operate in the depth of 10 to 20 meters upon the pump capacity. It varies as the capacity of the plant. So the pumps normally they are hang from top, hence the bottom can be accessed through a gap between the pump and the floor bed. However, the gap is so small that the minimum dimension, that is like about 900 mm, which is available through maybe drawings available at the power plants. So through that approach, we have to consider for inspection. Normally, the chambers in the pump are narrow, hence the movement is very much constrained. As I told already, the water normally gets muddy or it's turbid, mixes with oil, grease. Hence, it is very difficult to see many things. So, how we designed our things that will slightly go into this. So, these are few notations as I have mentioned. We have considered the velocity and the drag coefficient along with the lift coefficient, how the system will have different dynamic these characteristics of the dimensions perpendicular to you. So this velocity and all will come later on. So accordingly, we come with the thrust and power of our system. So that this detailed design methodology, we also considered the buoyancy, then the drag force, similarly the lift force, and having then we calculated the thrust, power and thrust similarly. So I am not going into detail of this, so this will take little more time. And this is one simulation what we arrived at. This simulation was also before we have presented in a NTPC conference that gives us this hydrodynamic analysis about CW pit or some inspection robot for application in power plants. So here what we have did is we made a modified model or a model of a system where we have simulated this in a CFD environment. So this is all the envelope what we have taken, length of 0.5 meter to height is 0.4 meter with around 0.8 meter, that is, and the propeller we have simulated. So these algorithms we have used, and what in the numerical analysis we carried out with the steady state K turbulence model, K epsilon turbulence model, and the relative velocity we have taken as 2 meter per second. That is through, of course, the inputs taken from the thermal power plant people or NTPC people. So, and the boundary condition here we assumed is velocity inlet, outlet as a outflow, that with no slip boundary conditions for one. So what we observed here is that the pressure acting on the surface of the robot, that is on the front side, is very high pressure because of the stagnation of the fluid. So this is what's very much in line with how we are designing the outer periphery of the robot and all, or the casing of the robot enclosure. Similarly, the velocity contours are also in order. What drag we got is on the robot body is about 1.55 drag force, and for calculated for 78.6 meter. So similarly, this is the CAD model of our overall system. This is about 450 450, 425, 360 mm without millimeter. These dimensions are there. Similarly, we have used the 350 watt brushless thrusters, speed of around 0.5 to 1 meter per second. So the communication is through sensor as well as camera data communication through serial communication. Similarly, sensors like IMU, sonar, camera are used in the this system. Camera with some illumination are also there. Of course, the arm, servo arm, we have used 1 degree of freedom. Of course, extra lights are also used, 4 numbers. And this system is totally tethered cable with command and control station. Tethered cable length was around, and similarly, this patent application is also filed very recently for this system. This is the actual system you can see. This is the prototype for inspection and the prototype for intervention also. And this is the, on the right side, you can see the control circuit, like how main board is the Raspberry Pi onboard computer, or through flight controller. We are controlling the all 6 thrusters, and this is the basic diagram how we control the overall system. Similarly, these are few glimpses of the field trials or experiment conducted in the thermal power plant, Bihar. So what was our objective is to inspect some CW pumps. So 4 number of pumps were actually shut down, so there was hardly any water flow. So the inspection hole what we got is 600 to 750 mm. The depth of the water at that time was about 7 meter. Turbidity also similarly. Uh, the impeller was located at 5 meter from the entry, that is below, and this you can see this is the pump, and these are the impellers subjected to impeller. These were, and this is the inspection area from where the robot actually was inserted, and this is the sump area for inspection of the grill gate at the sump side, and this is the pump side, and below this we can have a pump. So this is actually in a solid model, you can see easily. We have a command station on the ground, and then this is the pump area, which is the
Umesh, you can
sub.
just speed up for your conclusion.
Yeah,
Last
yeah.
1 or 2
In 2 minutes, I
minutes.
will be finishing.
Sure.
Yeah.
Okay.
So this robot will be going downward and then inspecting the pump area, and then coming back. So what we results we got, that these are the some sonar images. So what we can see the impeller at about 1 meter to 1.5 meter from the system, and these are few what we observe is the image one is some marks on the concrete wall, and if you can see the screen gate also, and we found the inspected this impeller also at the bottom, and these are some haze image or dehazed image what you can see. So I would like to conclude here that the presently the human divers or the manual inspection, it takes a lot of time. So the what our aim was to develop a robotic system for inspection of the CW pump area, which is a constant space. So the robot is lightweight, portable, as compact for transportation, and an entry through narrow opening is possible, and we have taken sufficient safety measures. So with this, the underwater images what are dehazed using the AI-based techniques for identification of the objects of interest, and then the developed system has been field tested in one of the operational, as I told, one Indian thermal power plant, NTPC power plant in Bihar, and which was overhauled. And what we observed is another small limitation of this is that the present system is capable of capturing propeller image within the very close vicinity, that is less than 1 meter. The turbidity of water was 16 NTU with sufficient, we have some illumination also. So hence we an underwater laser sensor or underwater ultrasonic sensor, or sometimes a clear box can be used for more minute inspection. So that will increase the dimension of the robotic system. So this is one what was our observation, and also we have found that the configuration and the construction of each CW pump or a plant or cooling water pump, sump or pump is very different from one plant to other. So the operator has to understand the plant configuration, the construction of the walls, and the drawings beforehand. So that takes little more time. Then only, because since this is a teleoperated system, and battery has to be charged several times, because we have to have the longer, we have to take longer operations, and hence AC power is required for the control station. So that's how I conclude my presentation. Questions?
Okay. Okay. Yeah, it is well in time. Thank you, Umesh.
Yeah.
And with this, it is open for questions. I just check the chat box too, because sometimes people write there, and Q&A. Yes, it is open to questions, and by the time, yes, Umesh, you can keep it connected. Sometimes it helps. Okay, we'll see how what type of questions. Actually, by the time everybody writing, I am interested to know, because of course these are very practical applications. So my direct question is your design, because you have already shown many of such designs, so which are available, and is it inspired from some specific one, or you would like to say, I mean, just to make it indigenous, or would you like to compare with some existing one? Like, how do you see which aspect? Particularly, I'm interested to know about the mechanical, about the architectural plan, uh, like not the sensors, but about the mechanical architecture.
Yeah, as far as
Whatever you have
mechanical
planned.
aspect is concerned, ma'am, because one major limitation or issue with the globally available, of course, this is available in the literature also. Sometimes these CW pumps, the walls are concrete walls, and sometimes we get very hard objects or maybe these grill gates and other so steel object with the plastic part, and the robots get damaged or they cannot survive the what you say the plastic or the plastic part. So in
Okay,
that
so
case, what normally we do here, we have gone with the aluminum structure. So this aluminum structure, which is very rigid in this sense, and of course it has got a rubber padding also, so that at sometimes some shock it absorbs. So this way also this has become a little bit compact also, because
okay,
though
so I agree, but you mentioned about compact, but in totality, I would say in the paper, it gives us a very good idea regarding the overall picture of what all aspects it has.
yeah.
But somehow, if the readers would like to know, like it is so interesting, but we would like to know the details, because for example, you mentioned about the design, but none of the aspect was mentioned in depth, at least for this paper. So it would be nice if any reference papers you can mention later in the chat. Like if you have any detailed design in any of the other paper which you might have given. I mean, just for the readers to know. Right?
Yeah,
For example,
ma'am,
because you mentioned it is lightweight, but it is just concluded, which is not connected to the presentation you have given. How it is, how
yeah,
can you say it is
yeah.
lighter, it is weight?
Just to
Yeah.
I can share, ma'am, this uh, I can
Hello.
share actually this patent we have recently filed. So I think this is in the open patent 2021. So this number is there. Anybody can write down this number 202111029400. So all design aspects are means how we have arrived at the mechanical structure and the
Because
this,
was it as optimized from some perspective regarding the weight? Like how you have designed each component. There are so many components
yeah,
inside.
well, as such, optimization is not yet means done. But the thing is that this with this structure, we have actually developed so many structures, and then based on the like our
Experience.
experience and this optimal structure we have simulated, and this paper which was
So
presented in
that
the
means,
University Congress.
shall we say, Mish, because that means there is certainly a chance of reducing the some sizes or some width or some many of the geometrical features which can be altered for even improved design. I mean,
Yeah,
then
yeah, yeah.
there is still a chance because you have given a concept design, I would say, and which is complete in nature, and as its dimensional and other
Yeah,
features are required, they can
application,
be further optimized.
depending on the application, you can always scale up or maybe scale down. But this was specially for one NTPC sort of like application. So there
Yes, we
was a
have a
requirement.
question.
Yeah,
I'm sorry, I'm just
yeah,
cutting you down because there was a similar question also.
yeah.
And any comparative study carried out in existing system design and inspection methods? I think this is exactly what I
Yeah,
was asking. Can you please answer?
this is the overview of the systems what we have studied. This is you can say the ECA high tech both models. Okay, then Predator 2, that is the remotely operated ROV. Then Deep Tracker, there are two models. So similarly, dimension wise also we have calculated
No,
the
actually,
study.
direct question is there any comparative study already done? Yes, of course, you have inspired from these and developed your own system. But the direct question is there any comparative study, may it be related to weight or maybe performance, some performance criteria? I think that probably is coming up. At present, it is
Yeah,
at least
actually,
not
ma'am,
sure.
I did not come into like I have not seen any comparative study, but there may be some studies since we have studied some systems like this, underwater systems. There will be some.
Okay, yeah. So this was a question from Selva Kumar. I think it is yet to be done at their end, and it is not yet presented. Yeah. Okay. So with this, thank you, Umesh, and your team for presenting this. And with this, we can ask you to just stop sharing the screen, and we can move to the next participant. Thank you very much.
Thank you.
Yeah. Next, we have the presentation from paper ID. One second. Yeah, it is 79 by Deep Narayan Ray, and the paper title is Slim and Expandable Header Inspection Robot for Remote Visual Inspection of Boiler Headers in Thermal Power Plants. Yes, hello, welcome Deep Narayan. You can unmute, please.
Yeah, good afternoon, madam.
Yes, good afternoon, please. Please share your screen. It is all audible.
Is it visible?
It is, and now it is in the corrected mode. Very right. You may please start.
Yeah.
So, take your 13 to 14 minutes as if we are just
Okay. Basically, this was another initiative to provide application to these hazardous areas, as my previous speaker spoke out. So we all know about the boiler header of any thermal power station, and it's the most important part, basically critical pressure component, where both the pressure, high pressure and high temperature is there, mixture of the steam is there, and all the time it is under constant pressure and temperature. As a result, it is very much vulnerable to crack and other high temperature and high pressure corrosions and fatigue. So another thing is that but these power plants most of the time have to run over the year. Only a particular time of the year has to be will be there. The power plant has to be stopped, shut down, and overhauling or routine maintenance are there. So only that time you will have to inspect the headers, because from the boiler, the high pressure, high temperature steam directly enters the header, and from thereafter it goes to the turbine. All of you know. So if some foreign bodies or say on scales is formed on the surface of the header, and if some way the steam blows those foreign materials to the turbine, it will be huge damage. And sudden shutdown of a power plant, it's not only a loss of revenue, but it also gives catastrophe to the national power grid, and suddenly the whole country may be in total darkness. So the conventional way is to use remote visual inspection using, this is known as, we call it a boroscope. Basically, this is commercially available worldwide, and a renowned company is also selling this. But while using this type of systems, it has been found that the length is very much restricted, say 5 meter, 10 meter, and obviously the tip of the camera is lying on the floor in internal surface of the header. So it is not possible to have a view, say internal diameter of a header starts from 550 and it can continue up to 700 mm. So it is very difficult, as well as the illumination by the tip of the camera is not sufficient. As per, there is some recommendation by this IS or European Union where this standard has been mentioned around 600 lux. So which is very difficult to obtain by using this type of system. So this was the thing in our mind, and you can find two models of the boiler headers where either you have to enter the header through this type perpendicular entrance or parallel entrance, and maximum diameter you can obtain is up to 90 mm, not more than that. So it is very difficult to approach inside, and you will have very less time to inspect the inside of the header. So we started looking what are the work already done worldwide. So we got a number of systems starting from GE, Alstom, which are world leader in this power plant domain. So these first three, figure 1, figure 2, and figure 3, these are three types of header robots which are being used either for drum inspection or maybe the surface inside of the boiler header, that is the water tubes inspection. And another is that this is another one fast platform. It is also by Alstom, basically to identify the surface of the water wall tubes, that is inside the boiler, but not inside the header. So, and also the last one is from BARC India. So they are also most of the focus of the work were to identify or measure the thickness, wall thickness of the boiler headers, water wall tubes, that is inside the boiler. And the boiler header is generally situated on the top of the penthouse or boiler house above the boiler. So it's around 80 meter high from the ground. So none of these robots are attempting to inspect the header itself. But thereafter, we got two works from this Malaysia National Technical University, but those are still in the say you can say R&D stage, and still there are some of the systems, they have some little bit limitations, though they have tried a lot. But the issue is that as I told you, the header inside header diameter may range from say 350 to say 600, etc. So but here as they designed, it was only around 120 mm the camera can reach. But it is always better if you can place the camera along the central axis of the header. Okay, so it may be the dimension may be from the floor or from the internal surface of the header, it may be 350 mm or it may be 250 mm. So similar dimension you have to achieve, means as the height of the
I'm
camera.
sorry to intervene you, Deepan. I would suggest that you can come, because already half of the time is over.
Okay,
so
okay,
because the
okay.
time is short, you should actually show your work more.
So with this, this was our main objective, that we have to enter the header through a handhole diameter of 75 to 80 mm. And thereafter, you have to expand. You can just see at the bottom what are the challenges. So you have to expand your system either 7 to 10 times, 7 to 10 times from its initial dimension. Then only the your visual inspection is possible. Apart from that, you have to have a 360-degree planar view. So with this, these are the design methodology. This is very known to all of you. So with this, we have a lots of design means design iterations, and thereafter, obviously, we got some of the components. And the main difficulty was, as I told you, you have to expand your system 7 to 10 times. So it was very difficult to reach or achieve such magnification from a very miniaturized one. At last, we have developed a basically two systems are there. One is, as you can see from the right bottom image, one is driven by a single motor and another is driven by double motor. But the single motor system, depending upon your entry diameter, you can just interchange. Either you can use this 3 degree of freedom arm, or you can use just the this is a LED lights, nothing but strip, LED light strip, and accordingly your entry dimension will guide which robot had to be used. So two different sets have been developed, and this is the bottom one. The bottom one is the double motor system, as I shows in the cross-sectional view. And obviously we have achieved the minimum dimension of entry 68 mm, 74 mm, and 87 mm. And these are the overall specification of the system, along with the images of the two prototypes. And these are the conventional generalized architecture where we have used either single motor or double motor. And apart from this, a numbers of sensors have been used depending upon the requirement, depending upon the functionality of the system. And apart from the lab scale trial, again we have a number, means field trials at the nearby NTPC plant, where you can find out the system is being entered through a handhold of a boiler header. Generally, it is sealed during the operation of the header, but due to inspection, it was cut, and the robotic system is going inside. And thereafter, you can find out on the right extreme image the internal dimension of the header, and the camera center of the camera has reached the central axis of the header to get a very good view of the overall header. And obviously the first one is that, as I told you, sometimes we have to use the same system. We have used a forward movement and reverse movement. So it was very much essential to study the both the clockwise and anti-clockwise characteristic of the motor, so that there is a very little bit deviation which can be corrected by the control algorithm or the software, etc. It's thing. And obviously, as I told you, the recommended illumination has to be made. That has been tested in the laboratory. And finally, the most important thing is the distance. So the right bottom image can see from that you can find out during, this is the truncated GUI of the system, from where you can get the distance from the entry where the object is being placed. So these are the some of the foreign bodies we have seen, and this is the second image, is that we have got the surface irregularities on the inside the header before it is steam blown away. And obviously during some workout, the washer is there, lumped mud is also there. So these are the distance measured from by the system itself, and what are the surfaces, what are the things, foreign body or items that has been displayed here. So this is the first go of the system. So obviously the conventional video image, means our system is far better than this video imagoscope, and it can capture the raw image of the system, as well as the system itself uses image processing techniques to identify the foreign objects or any irregularities within the system, as well as it can provide you the exact means approximate distance from the entry, how far is the foreign body or these irregularities are there, so that you can take care of. However, we are obviously doing some reliability study of the system. One of my co-developer from NTPC, Dr. Mondol, is there. So they are already using such system in the real-time field, so they can give you a better view of the developed system. With this, I end up my presentation.
Thank you, Mr. Deep Narayan. And with this, we open for the question answers. You can keep the slides. Sometimes they help to answer the questions. Yes, I can see not people probably be writing at this time. So yeah, may I know, like here you have talked about the reliability or even otherwise, like any comparative study from your end, because you're from the same lab. It is interested to know. I must say that we have developed the systems which will be helpful, and improvement is always possible. But still, how do you see, like, what is the major one selling point, what we can say that is comparatively better than the existing or comparable than the existing? Is
Actually,
there any
madam,
such observation?
but two things just to say you. Basically, there is no such system. You can from the literature survey. There is no such system commercially available. This is one. And number
From
two
the
is
size perspective, because you have mentioned a few which were there in the literature survey. So may I know from the size perspective? Because okay, this is miniature version.
yeah. Size from the size perspective, they are still on the higher side. Yeah, Dr.
Deepnarayan,
Yeah.
yeah, just to add, ma'am, actually the situation is what he was trying to tell. He just, kept all the available robotic device which is used in power plant application. But if you see their high size, no, it is not. I mean, most of them are either heavyweight, more than 20 kg, sometimes it's 200 kg, or size wise, it's really big. But our entrance is only 70 mm. So miniaturization was the biggest challenge, number one. Number two, the device which we are inspecting, it has to be full. The device which is going and uh, inspecting, and then it has to come back, because nobody will allow you to leave the power plant with.
Okay, so related to that, thank you, Avijit. But related to that, because is there any study which is required then? Because you need to, have a trade-off between the size and the probably the battery or the actuators it is carrying its own size also. Sometimes we need the size to accommodate the battery or accommodate the other aspects which are required, maybe the better camera. So because of the because of compromising the size, which is good for us that it is miniaturized, is there any compromise on the feature of say any coverage of the camera or any battery, its activation time, etc.? Is there anything which we'd say is limitation?
No, compromise means earlier device, what you are saying, it's very similar to endoscope, which can enter through 8 mm. So field of view, illumination, everything has increased, because now you are putting a device which is relatively far bigger size than the earlier endoscope, which was 8 mm in diameter. So as now it can enter through a 70 mm diameter. So illumination, you have kept enough so that you can illuminate the entire inside. And
okay, then related to this, okay, just one more curious question, because I do have time and there is nothing from yet from the participants. Okay, then what about the reach? Because he has mentioned something regarding that we can check its location, from outside. But is there any? Can we say anything about the reach, where it can
no,
go,
it has
and if there are
reached,
turns anywhere?
earlier the device what we are using, no, that was a general purpose tool for remote inspection. So that's why they have kept 7 meter, 10 meter, like that. It's a commercially available product for general purpose application, but this is designed for specific application. So we have kept the length as much as the header length is, which is 25 meter. Because it's a customized tool, so we have
for that specific
but only challenge what we are facing, we have reached the least possible miniaturized angle where the motor is available in the market. So if you can further miniaturize the motor, then we can cover all the different size of power plant. Because what he was saying, no, entry from 70 to 90 millimeter. But now our requirement is we want to make a device which will enter through 70 meter only with all the torque capacity and everything. But there we are stuck with the available motor.
No, that I agree. That is always
Yeah.
the limitations, and that is where we can always think of further improvements. But yes, making the working model always help and encourage others also. Thank you, Avijit and Deepnayal and all your teammates. Thank you very much. So with this, we can move to the next, and you can, yeah, one
Yep.
second. So
Thank you.
next,
Thank you very much.
thank you very much. So next with us is our ID, paper ID 96. It will be the fifth presentation for this session, and it will be done by Saurabh Chaudhary. And the title is Robust Control Strategy for Reactionless Maneuvering of a Dual Arm Space Manipulator.
Good evening, everyone. I am Saurabh Chaudhary, PhD student from Department of Mechanical Engineering, IIT Jodhpur. Today I am presenting my paper, A Robust Control Strategy for Reactionless Maneuvering of a Dual Arm Space Robot. And the co-authors of the paper are Shreyas M. Patel, Prasad N. Dal, Dr. Shyamki Joshi from same Department of Mechanical Engineering, IIT Jodhpur, and Dr. Niladri S. Tripathi from Department of Electrical Engineering, IIT Jodhpur, and Dr. S.V. Shah from Mechanical Engineering Department. Mechanical Engineering, IIT Jodhpur. So in future, we need some special missions to inspect the satellites, repair the satellites, or assemble something, some structure in the satellite, or we want to review the long-term satellites in orbit. And sometimes some debris may come in the path of the working operational satellite, so that need to be removed from the course of the current operational satellite. Here you can see four pictures. So these are showing the in assembly in orbit operations. In figure one, we can see one space of one structure is assembled in the space. In the figure in the picture B, we can see robot is trying to capture a decommissioned satellite so that it can be deorbits, or it can be sent to the graveyard orbit. Or in picture C, we can see one satellite is repairing the another satellite, and in figure D we can see the birthing or birthing or docking of a small satellite from a mother satellite. So all these activities will be autonomously carried out by a robotic.
One second. I'm sorry to intervene, Saurabh. We are at the first slide, yeah, right?
Ma'am, second slide.
Just move your slide. We are not able to see the slides.
Yeah,
the change of movement.
Anyone
No.
can?
Ma'am.
Yes, Rajiv.
I could see.
Okay, okay. So I'll just, he's at the second. You can see that. Yes. I'll just come again. Okay. Yeah, please continue, Saurabh. Thank you.
Sure, ma'am. So as these objects, those are need to be handled or maneuvered having different masses, and sometimes we do not know about the masses, how much it has. So only we have an approximation about the masses. So in this case, a robust control strategy is required to carry out the manipulation task by the robotic manipulators. So when we move, the one problem with the manipulation of the joints here in the animation, you can see when the arms are moving, the base get disturbed. It gets rotated about by some angle. So here in this picture also we can see when this manipulator try to capture this point. Now the base is getting disturbed. So due to this is due to the reaction movements are transferred to the base, and the base attitude gets disturbed. By this, we cannot completely capture. We cannot capture this point perfectly, and sometimes the high gain and the communication between the satellite and the Earth also may get disturbed due to the high gain disorientation of the high gain antenna. So, in order to make the base attitude close to zero, while maneuvering the arm from some initial position to some final position, it is known as the reactionless maneuvering. So reactionless maneuvering is basically the maintaining the base attitude close to zero. Our problem statement is to develop a robust control strategy for reactionless maneuvering of 6 degrees of freedom dual arm space robot with varying end effector mass. So in the figure 1 shows the dual arm 6 degrees of freedom robot that we have considered in this work. For finding out the robust control, we have divided our control strategy in three portions. First is the modeling of the dynamic system. Second is finding the constraint for the reactionless manipulation. Third is the control formulation. In the first modeling portion, first of all, we will derive the equation of motion of the space robot. Then we modify the equation of motion in the term of joint motion. And in the second portion, the joint level and the task level constraints are obtained using the linear and the angular momentum equations. In the fourth, in the last, the robust control problem is defined, and the solution of the robust control problem is obtained using the optimal control problem by the linear quadratic regulator problem, and then the robust control problem is controller for the robust control problem is obtained. Here the equation of motion of n degree of fixed base, n degree of robot or the earth based robot manipulators is given by equation 1. Here Im is the inertia matrix of the manipulator, q m double dot is the acceleration of the joint, c consists of terms of Coriolis and centrifugal forces. Tau m is the joint torque. Similar to the fixed base robot or space-based robots, space robots are also having same structure, but the structure of the inertia matrix and are somewhat different, because space robots are the floating based robots, so base will also come into the picture. Here IB represents the inertia of the base, inertia matrix of the base. IBM represents the coupling inertia between the base and the manipulator. QB double dot represents the base acceleration. CB and CM represents the velocity dependent terms. FB and FE are the external movement or the external forces acting on the base and the end effector. JB and JM are the base and manipulator Jacobian. Tau m is the joint torque. So if we are assuming there is no movement or forces acting on the moment, and the moment and external forces are acting on the base and the end effector, and eliminating base acceleration from equation 2 will get the modified equation in 3 in the terms of joint motion. The linear and angular momentum of the space robot is given by equation 4, and this IB and IBM matrix is same as obtained in the equation of motion. That is equation 2. So this IB and IBM and base velocity is represented like this, where VB represents the linear base velocity and omega V is the angular base velocity. So we assume our robot system starts from there. So in that case, linear and angular momentum are 0, and we need 0 attitude disturbance. For that, the base angular velocity should be 0. So after imposing these three, after putting these three conditions in the equation 5, we'll get the constraint for the reactionless maneuvering. The end effector velocity or the end effector velocity is defined by the equation 7, and by combining the equation 6 and equation 7, we get the task level constraint as defined in equation 8. On performing the feedback linearization on system on the modified equation of motion, we get the control law, and after that, writing the modified equation of motion in the term of this obtained control law, the system dynamics can be represented in the canonical form as represented in 10. This is our robust control problem, where HX and FX contain all the uncertainties. So here our aim is to find to obtain a control law that stabilizes this system for all the uncertainties HX and FX, satisfying these two conditions. And for more details of stability analysis and other readers can refer to this book, Robust Control Design and Optimal Control Approach by Eflin. So mainly our work is based on this book. Now the robust control problem is solved using the optimal control problem. For that, nominal system of the equation, the nominal system of equation of system 11 is considered. So here our aim is to find a optimal control U that minimizes this cost function. Cost function 13. So the solution of the optimal control problem is found using a linear quadratic regulator formalism, where by substituting by taking a bound on f max square like this, and the optimal control law U is obtained by solving the algebraic Riccati equation as given in equation 14. So this ensures the regulation of all the joints to a steady state, and when we want to track our joint from some position to another position, in that case the states are defined in the error domain, and the optimal control law for tracking we obtained in equation 15, and where E represents the position error between the desired and between the commanded and the computed one. We have performed several simulations like regulation of the checking the regulation of the joint, it is going to the steady state or not, and maneuvering from one given initial position to final position using joint level and the task level constraints. So table 1 shows the consists the space robot parameters, link length, mass, moment of inertia, and everything for both base and both the arms. And the table 2 consists the initial and the final positions of all the joints, and a cycloidal trajectory is commanded to the all the joints to follow. So in this simulation, we can see the manipulator is moving from one position to another position, and base is not rotating. So this ensures the reactionless maneuver. Next, in this figure A, the right side, the top row shows that error between the commanded and the computed one. So as it in the order of 10 to the power minus 3, so we can say it is almost tracking the same trajectory. It is almost tracking the commanded trajectory, and the error theta 1, theta 2, and theta 3 are for arm 1, and correspondingly the joint torques for all the joints are given on the bottom row. So we have obtained similar results for the second arm also. And here in figure B, we can see the positions and orientation of the base and the angular velocity of the base. So angular velocity of the base is more concerned for the reactionless maneuver. So as we can see, it is in the order of 10 to the power minus 4. So we can say we have achieved the reactionless maneuver, or the maneuvering during the maneuvering of the arm. So the base is not getting base attitude is not getting disturbed. So these results are for using joint level constraints. So here the controller, first of all, the controller is implemented so to see the regulation, like all the joints are going to the steady state, or the system is stable or not for stability. And so we have performed the simulation and we got these results. So top row, this left side 2 cross 3 represents the joint positions, and right side 2 cross 3 represents the joint torque. So we have simulated all the result, all the everything for varying the end effector mass, that is m equals to 0, 15, and 25. This m0, 15 equals to 0, equals to 15, and 25 represents the different graphs. So we have changed the end effector mass and then repeated the simulation process. Here, and also we have performed the simulation using the task level constraint, and similar results are got similar to the joint level constraint. So here in the top row, we can see the position and the orientation of first end effector of the first arm, and the joint torques of the first arm. And in the figure B, we can see the angular velocity of the base is in the order of 10 to the power minus 3. So we can say the base is not rotating, base is not rotating, or its attitude is not changing, so it is almost near to 0. So these results are obtained by using task level constraints. So in this work, we have developed a feedback controller based on the robust control strategy, and the robust control problem is solved using the optimal control problem by using the linear quadratic regulator problem formalism. And here we have taken a maximum bound on the end effector mass is 30 kg, and the other parameters are standard units and the dimension, and we perform this numerical simulation for the regulation and the reactionless maneuvering using the joint level and the task level constraints. Thank you.
Okay, thank you, Saurabh. It was in time, and questions you can keep them. Keep the slides. Yes.
Okay, okay,
shared yet. Sometimes it helps. Yes, for time for questions, and let me check. Okay. So we do have, yeah, starting there are so many. Yes. So in the cost function, have you given some weights to some of the outputs?
No, ma'am. So
Okay.
here.
Yeah. Actually, in the beginning, I missed, but yes.
Okay, these are the cost function, and when we convert it in the linear quadratic regulator problem, so these are solved using the Hamilton-Jacobi-Bellman equation. So no weights are given.
Not considered. Okay,
Yes.
we have a couple of more questions. 3. Next is on slide 6. If you just go to slide 6, can you explain that again, please? You said you assume the base, or it's the target.
No, not target. It is the base. The external forces acting on the base or on the end effector mass. So those we have assumed 0. Like
And
on the
have you
base,
planned for? I think this was clear to the person who has asked the question. But the next question, Anubhav Dogra is asking: have you planned for which actuators are you gonna use for these applications? Like,
actually,
is there any?
Yes. This is the simulation question. So we have hardware also for a space robot. So in that we are using Dynamixel MX64. So that hardware demonstration, it is a future work. So
Not yet, but you have planned for.
Yes, ma'am. Actually, we have the space robot setups having MX64 Dynamixels. So that we want to implement this work on that hardware.
Okay, I'm coming to one or two of my questions. Anyway, one more question from Sandeep Kumar. Are the weights and the dimensions of the links are arbitrarily taken or taken from some real examples? Like now you are mentioning that you're anyway you have already developed the dual system.
Yes.
So,
yes.
But yes, what about the dimensions and the weights of the arms?
They are taken randomly, but as the base is heavier, so we have taken the mass of the base more, and all the links having the similar masses. But when we implement,
let us talk about the links particularly, not the base.
Links.
Yeah,
yes, it is taken arbitrarily, not any experimental, not from any present system.
Because then it will be far from your actual experimental.
Yes,
experiment. You have to, because maybe you've just taken something and far more improvement is then possible. So then you said you've just taken something to try the controller or to complete that. Okay. By the time,
but only we maintain the similarity, like symmetry between all the masses and length, mass and length in all the links.
Symmetry. I'm sorry.
Means
between the
all
two arms, you mean?
Yes. Between the two arms,
that is
they are
for
having
probably
same.
the balance. Normally, we keep the same for dual arm.
Yes.
Right. But otherwise, it's okay. We have a couple of more questions. So first is Venkata Rangan, and did you simulate and check the output of this? And which simulation environment is used for that?
Ma'am, we have used the MATLAB for simulation. So this is the simulation using the joint level constraint.
And how do you... Okay, 1 second.
Ma'am, it is not a... Yes, I can show the simulation.
No, actually, it is related to my question also, because it is also asking which application are you motivated for? For example, here you are just giving this particular trajectory, what you have shown.
Yes.
In fact, given this is like from which perspective you are taking the symmetry, and this trajectory is not. If you can connect it to some specific reason. This is the question.
Trajectory we can provide anything. Just for the simulation purpose, we have given a cycloidal trajectory, and when we are performing in the task level, so for that end effector we have given a quantic polynomial. So as we have checked, giving the different trajectory to both the arms, and the similar results are also obtained. We have not mentioned.
Have you tried for arbitrarily different, because it gives a bigger difference between when we change and the type and their movement and even their extent trajectory, that there will be differences. So I think more simulations, or maybe if you have already done such on different trajectories? Have you done such comparisons, or
Yes,
at
ma'am.
present
We have
this is the same?
yes, we have given a cyclic and a cycloidal trajectory to both the arms.
Also,
One
so
arm
it
is
would have
having.
been better to add also here. I mean, I don't know. I'm just suggesting.
Actually, this was not added in the paper, so
Hmm.
I can check if I have the graphs. I
Okay,
can
so we
show.
have another question. If the external forces are neglected during design, then is the robustness of the controller justified? Actually, this was my question, and I'm just connecting my questions to this so that we have limited time. Like,
Yes.
how do you justify? Because the main point of your title is that it is robust. So how do you
So, ma'am,
justify? Which
robust
slide?
in the main, yes, we are considering the end effector varying masses. So we have the different masses like here. So it is taking, it is,
Now we are talking about robust controller.
yes, ma'am. So we have only considered the masses at the end effector, whatever the end effector is carrying. And for the base, so if the base is this, so some forces we have neglected. So for that, we are assuming the jet thrusters are there to balance the reaction forces. And for the moments, for countering the moments, we have implemented the reactionless maneuvering.
Yeah, actually, you were talking about robustness and reactionless. So basically, it would have been great, or maybe again I missed that if there is any disturbance or if there is
Yes,
any
like
change.
ma'am, here we can see like here the robots need to capture this one or maneuver if it is captured. So it is captured here. So let me change the color. It is, you can see it is captured here. So it need to be moved from this position to this position. So in that case, if our joint torque controllers are designed to carry only 10 kg, and if this object is having 15 kg or 20 kg, then at that point our actuators will not able to manipulate this object from this place to this place. So this is the first task, that is for the robustness.
Okay, okay.
So we are taking 30 kg, the
So I
maximum
think
limit.
the last remark, I agree, and the last remark is
And
from Udayan Banerjee. So would you like to say that the controller robustness is with respect to the varying of mass? Yeah.
yes, yes, ma'am. Yes, ma'am.
Okay. So anyway, interesting presentation because we have got such a good number of questions for you, and
Thank you.
we wish you good for the next work. And thank you very much, Saurabh. We move to our last presentation for this session.
Thank you so much, ma'am.
That will be the paper ID 97 by Debabrata Sarkar, and the title is a reinforced soft bending type actuator with improved performance and force sensing.
Yeah.
Yes.
Am I visible?
Yes, you are Soman Sen. So it's a change in this one?
I am Debabrata Sarkar.
Okay, okay. The ID, okay, here it is shown. Okay, yes, it is visible. You can keep your presentation in the presentation.
Okay, fine. So my presentation is visible, right? Fine,
Right.
fine. So let me start. Okay, so hello everyone. I am Debabrata Sarkar, along with my co-authors Shagnik Chakraborty, Mr. Amanawara, and Dr. Shoman Sen from Central Mechanical Engineering Research Institute, Durgapur. So let me take this opportunity to present our article, which deals with the design analysis and experiments of a reinforced soft bending type actuator with improved performance and force sensing. So most of you know about the emerging field of soft robotics. So let me discuss why did we really take up soft robotics? Because it helped us to biomimic the various living creatures. The inherent compliance and flexibility in such soft robots allows them to be used near human operators safely. Also, they find applications in search and rescue robots as well as in various assistive and rehabilitation devices. So, regarding the associated literature, we should say that pneumatic actuation is a very popular strategy for actuating the soft robots, and this is our previous attempt in developing such a soft bending actuator. However, it shows excessive bulging, which makes it prone to rupture when used in constrained spaces. To solve this issue in literature, we found several fiber reinforcement techniques. But while the single helix reinforcements lead to skewness in the actuators, the double helix reinforcements are quite intricate and quite complex to be fabricated. So we were in search of a convenient fabrication technique for reinforcement. In literature, the simulation, certain finite element simulations have been successfully performed for such soft robots. But when we used such data of material properties from literature in our previous attempt, we were really disheartened to see that there was too much deviation between the simulation and experimental results. So we decided that it is of utmost importance to characterize our own material, since it depends upon the range of strain in which we are characterizing, in which we are operating the actuator, also in like how we are curing it, temperature, etc. Regarding the soft sensors or soft or flexible sensors used along with these actuators, literature shows the use of carbon nanotube based, also conductive liquid metal based sensors, but these are quite complex to be fabricated. We found that this conductive flexible textiles could be a very good replacement of this. Our objectives were to develop a pneumatically actuated soft bending type actuator, definitely through convenient reinforcement techniques that will in turn enhance the force application capability and reduce the excessive bulging that was previously happening. Also, we would like to investigate the efficacy of the finite element based simulations in predicting the performance of the soft actuators prior to fabrication. Also, like we had planned to develop a customizable flexible force sensor for these actuators, definitely through economic and simple fabrication processes. So the actuator consists of a silicon main body, circular cross section of 25 millimeter diameter, overall length of 80 millimeters. It houses 3 cavities, or in other words, pneumatic actuation channels oriented at 120 degrees to one another, each having a semicircular cross section of 4.5 millimeter radius and length of 70 millimeters. The most important part of this design are the nitrile rubber O-rings that have been used here as the main reinforcement elements to reduce the excessive bulging. So through the section view of the actuator, we can see the working principle. When a single channel is pressurized, the material around the channel gets elongated both radially as well as axially. Thus, by virtue of the difference in material thickness on either side of this channel, a bending phenomena is being exhibited. Since on the outer side, a greater strain is experienced by the material and a lesser strain on the inner side. And as you see, that harmful radial bulging is really contained through the use of reinforcements. And a differential pressurization of these channels would definitely lead to a multidirectional bending behavior. So for fabrication, we had used 3D printed ABS molds consisting of the base, the cores, the side walls, and the core orienters. They were assembled together. EcoFlex 0050 was used as the silicon material that is available in part A and B, mixed in 1:1 ratio by weight, stirred thoroughly for 1 to 2 minutes, and further degassed to remove any kind of entrapped air in a vacuum chamber for 5 minutes. The prepared mixture was carefully poured in cavity and was kept for 180 minutes at approximately 27 degrees Celsius room temperature for curing. Upon curing, it was carefully extracted, and further the nitrile rubber O-rings were assembled on the respective groups with the help of silpoxy silicon adhesive, and PET tubes had been inserted into the respective pneumatic chambers for pressurized air supply. So this is our sensor that we propose. It generally consists of a 10 mm cross 10 mm conductive fabric layer that inherently comprises 63% cotton, 35% silver yarn, and 2% spandex. Over it, we had assembled 2 layers of velostat material. This material is actually impregnated with carbon black, and this exhibits a change in electrical resistance on application of a normal force over it. Further, another layer of conductive fabric, and both these conductive fabrics have been stitched using conductive thread that act as the electrical terminals of the sensor. And the total sensor has been encapsulated within another silicon, EcoFlex 0030, overall thickness of 2.5 millimeter. So this is our fabricated sensor. So we had characterized this sensor using a tabletop customized setup comprising of a probe and a load cell. We had performed quasi-static loading and unloading over 5 such cycles up to a maximum of 30 newtons. Linear range was identified from its result up to about 2.5 Newton. This shows the linear characteristic equation. However, we can definitely tell that it has a full range up to 30 Newton, but definitely it has some nonlinear characteristics. The resolution was observed to be around 0.2 Newton, and the sensitivity to be around 3.9 resistive strain per Newton. As you see in the video, it is quite sensitive and repeatable enough. So for finite element analysis simulations, first we identified the nonlinear material model, what I was talking about, for our specific material, EcoFlex 0050 through uniaxial tensile test. Following ASTM D412 protocol, up to 200% strain, we had conducted the experiments at 10 mm per minute extension rate. So out of all the nonlinear material models fitted, we found that YO model was found to be the best fitted to the experimental data. These are the corresponding coefficients. And for this material, the density was 1.07 gram per cc, and Poisson's ratio was assumed to be 0.5, making the assumption of incompressibility of the material. For regarding the mesh, we had used quadratic tetrahedral elements because this definitely gives us an advantage of accommodating the various complex shapes that these kinds of actuators can acquire. The element size of 1 mm was chosen based upon a grid independence study, and total number of 220,249 elements were used. Now, a very important concept, aspect of this simulations was that for the ease of meshing, this nitrile rubber O-rings were generally of circular cross section, but we modeled them as having square cross sections because it helps us in really meshing in the simulation Abacus environment. But in order to prevent any kind of difference in their functionality, their section modulus were considered to be equal and then modeled accordingly. Further, regarding the loads and boundary conditions for a free bending experiment, one end was encasted, the other was kept free, and a single channel was uniformly pressurized up to about 47 kilopascals. So the bending angle subtended was recorded and studied upon. Also, we had conducted another such simulation to study the axial force exerted by the actuator in block tip condition, where one end was encasted. On the other end, any axial displacement was completely restricted. And now in this case, all three channels have been pressurized simultaneously up to 30 kilopascals. And then the reaction force was studied to be the axial force exerted by the actuator in block tip condition. So these were the experiments of free bending, where the single channel was pressurized through proportional pressure regulator up to about 47 kilopascals.